Switch on. Good morning, everyone. If it will come now. Okay. Share now. Hello, share.
No, it's not shared.
Another is welcome.
And uploaded in there actually.
It's good. Can start. The old one shall I delete? It'll be confusing. All right. Can you hear me? Okay. So, good morning, everyone. So, welcome to the second day of our work meeting. So, sorry for the delay, 5 minutes early morning, and we are also seeing some. Yeah. So, we need more participants. So, myself, Sebastian Peter. I'm an associate professor in Jawaharlal Nehru Center for Advanced Scientific Research. Currently, I am in charge for photon factory beam line in KEK. It's all well said by the great leadership of Professor Milan Sanyal and Professor Chandrabas Narayana, and then Professor Mrinmai. So I'm also thankful to Mrinmai to give this slide. It's a learning curve. So here. I'll just give brief view of photon factory. This is the second phase going on, and then we have extension until next year, and we are going to have another 5 years. So work is going on. So this give a glimpse of what we have done. Last 10 years. And the JNCASR earlier, it was done by, it was coordinated by Saha Institute of Nuclear Physics, SINP. And currently we are actually, JNCASR is doing, basically all related to administrative roles. We are monitoring from here from A to Z, including the financial management also. So you can see that the journey started way back in 2010, April, started this beamline, under the leadership of Professor Milan Sanyal. And you can see him physically present there, multiple occasions, second time also. And this is an instrument, a dedicated instrument for any scientist who is working in the area of, the diffraction scattering related research. It's a beautiful setup, developed by, the team. And these are the experiments when we can done. The powder diffractometer and single crystal diffraction, high temperature and low temperature, wide range of temperature we can carry out in this one. And reflectivity and diffuse scattering from thin film, SACs and GSACs, can be done. Very good, it's experimental results you can get it. Reflectivity and diffraction on liquid surface and high pressure diffraction. This done by Professor Chandrabas. This is also a part of this one. And you can see the various components associated with the machine. As I said in the previous slide, you can set up the facility, depends on what experiments and you're working on. And you see, this is 2 cycles actually, started, some proposals, 15th June and 15th December. And currently the cycle is going February, March. We started February 29th and until April 1st. So this is currently going on. We have a couple of postdocs placed at the beamline Gorang, Manna and Pinku. So they are working there. Currently the experiment is going on. So the next cycle is going to start somewhere in October, December, but it's early, May, June, and then followed by October, December cycle. So these are the, the brief view of, the proposals we have received, a number of experiments we have performed. And you can see that the statistics given, how many, proposal, in terms of, so we accepted. So we had several, distinguished people, across the country, who involved in the panel reviews and everything. So you can see the list. We know each one, their contribution in the area, starting from Professor Sampath Kumar to Professor Krishna Kumar Menu. And so everybody contributed extensively in this one panel discussion. So we sincerely thank for their contribution to that. And the different phase, the second phase, different beam time, second phase, and we have this many number of days. So thanks, Minmay, for all this information. So it made my, so next, presentation so easy here. So you can see that for 190 available days last second phase project, and we have used 396. And plus 94 days set up the experiments, and this is overall excluding the current one. And you can see that one the different separate each experiment, single crystal, high temperature, low temperature, reflectivity, GSACs, liquid surface, etc. So it's kind of a good mix of various techniques. So some of the participants may not be aware about what are the experiments we can do. So this gives idea. So probably you can have a proposal in that area wherever you're looking for. And then another statistics. My wide experimental techniques used for a number of days. Another way of explaining. And across the country, most of the institute, used extensively, starting from south to north or west to east. So various, institute used extensively. 42 Indian institute, university, performed this experiment. That shows, the demand of the beamline is extremely high, and very happy to see that one. And you can see that number of publication. So, you can list that one, in 2029 publication, 2019, 25, 2018, 18, and followed by, 26 and 13. So total, 83 publication and 39 publications from the phase 1. Totally, it is 120, 130, it can be gone high, for maybe last few months, additional publications also, including we also published one paper. And this, you can see that impact factor of, the different journals. Starting from JACS, impact factor, more than 8 or 16. And then you can see that, good work, in a high profile journals, published by using this facility. And the phase 2 projects also, it's improved the quality much better. So you can see that number of publications improved. And finally, I would like to welcome to the second day. So please go through this, the presentations, and then make use of it. And we invite all of you to write, high quality proposals, and it can be, good, addition to your research activities conducting. With this, I would go with the first session. Sorry, any questions? Okay, so the first talk by Professor Abe. So he is XRF specialist. So he's going to talk about XRF beamline and studies at Photon Factory KEK. So he'll give you the glimpse of what are the experiments can be done and how we can make a collaboration in the direction of XRFs in addition to XRD that we are currently doing. Professor Abe, please.
Hi, this is Toshi at Photon Factory Japan. Do you see my slides?
Yes.
Yes, sir. Just swap the display, sir.
Okay, so, oops. It works?
Again.
Again.
Yes.
Okay. Now it
Yes.
works, right?
Yes.
Okay. This is Toshi at Photon Factory. First, I'd like to thank organizers for inviting me to this wonderful users meeting. And I also like to thank you for inviting me in September 2018. It was my first visit at your institute. It was a very beautiful experience for me. Okay, so I am a beamline scientist of beamline 9A and 9C, which are thus beamline at Photon Factory. And also I'm a member of executive committee of International X-ray Absorption Society. So all of my works have been performed by using X-ray absorption spectroscopy. As you can see, that can be applied to a wide variety of materials and phenomena like magnetism, surfaces, catalysts, nanoparticles, and even foods. So as you know, DAS consists of two regions. Near its region is called THANES, X-ray absorption near edge structure, and extended region is called XFs. So these two regions give us useful information. For example, THANES can give us electron states or chemical states of the element, and also we can estimate the bond lengths and the coordination numbers of the interesting element. So we can estimate also component fractions of sample by performing linear combination fitting of THANES by using standard materials. And importantly, we observe bond ranks and coordination numbers by performing precise XRF analysis. Okay, here we have, let's say, 6 hard X-ray DAS beamlines at Photon Factory and Photon Factory AR. And of course, we have some more beamlines for soft X-ray DAS, but today I'd like to focus on hard X-ray DAS. So we have 6 beamlines, and we can cover up to 40 keV, which means we can measure KH of cerium, and also down to 2.1 keV, so we can measure phosphor, sulfur, such kind of lighter element. Today, I'd like to share these 3 simple topics here. The first one is the study of valence state of calcium in calcium-nitrogen compounds. Here you see 5 spectra. This is the calcium KH spectra of these 5 compounds. And the formal charge of this calcium in this compounds is calcium 2+. But apparently you see the absorption edge positions are different. So the question is, what are the real oxidation numbers of these calcium species like in these 5 materials? So we can read the edge energy position of these 5 spectra like this. Here, for example, 4036.03 to 4039 to 68. So we know elements with higher oxidation numbers show higher edge energies. So we can estimate the oxidation number of calcium of these 5 components from edge energies. But the issue is we cannot measure calcium metal. It's difficult to measure calcium metal because it's burning. So we found a way to estimate the oxidation number of calcium species in these 5 compounds. I don't want to go details, but we defined electron biasing parameter beta related to based on the electronegativities. So by using this parameter and the relation between the absorption edge positions and this electron biasing parameter, we can extrapolate the edge position of calcium metal. For example, by using Pauling's value and also by using Merkin's value, we can extrapolate the edge position of calcium metal like this. So now we can estimate the valence state of calcium species of these 5 compounds. So by using this relation between the absorption edge positions and electron biasing parameter defined by S, oxidation number of calcium in these 5 components were successfully estimated like this. For example, here calcium ionic show 2+, it's totally ionic, and also calcium 2N shows 0.32. It means calcium in this compound is almost metallic. The next topic is somewhat demonstrative measurement of in situ depths at beamline and level 10A. Okay, this is the we see oxidation process of ruthenium nanoparticle on aluminum oxide. The red one is the initial state of ruthenium nanoparticle on alumina at room temperature before oxygen flowing. You see this is in the metallic state. And just after oxygen flowing, they are oxidized a bit and then gradually oxidized to almost 100% oxide state. And we perform danger analysis with linear combination fitting, and we can estimate the oxide fraction in the sample. Here, just after oxygen flowing, the oxide fraction is jumped up to roughly 70% at room temperature. And then with increasing temperature, the oxide fraction is going up to almost 100%. Like this, we can perform dust measurements under gas flowing and also temperature controlled conditions. So we call this kind of experiments in situ dust, which can observe chemical reactions of this kind of material in real-time manner. This type of in situ dust measurement are available at beamline NW10A and also at the beamline 9C. Beamline NM10A covers heavy elements like ruthenium, palladium, 4D transition metals. And at beamline 9C, you can measure 3D transition metals. So you can choose your preferable beamline, beamline 9C or NM10A for your interesting elements like 3D transition metals or 4D transition metals. So the last topic is the anchoring bond between nanoparticle and the spot. This is a catalyst for ammonia synthesis, ruthenium on calcium 2NH. This is a highly active catalyst for ammonia synthesis. Okay, we have 2 catalysts that they look similar. The first one is ruthenium on calcium 2NH, and the other one is lutetium calcium NH. They were created by Professor Kitano at Professor Hosono's group. They look similar, but the activity is totally different. The former one is much more highly active. The activity is more than 10 times, right? So the question is, are there any differences between the two which are similar at a glance? So we performed depth analysis to see local structures of lutetium of these two catalysts. This is the ends of these two catalysts. Lutetium in those two catalysts show the metallic state, blue one and red one. I mean, both of the two lutetium species are in were not oxidized. I mean, are in metallic states. Here's the Fourier transform over X-axis oscillations. Red one denote the lutetium calcium NH. This is less active one. It shows only lutetium interaction here. But the active one, lutetium-2NH, blue one, shows another peak here in addition to lutetium interaction. The careful analysis find that this peak can be assigned to lutetium-nitrogen bond. So we say that lutetium-nitrogen bond is clearly observed for highly active catalysts. Here's details of X-axis fitting for this catalyst. Here we have lutetium interaction, which is attributed to a bond inside the lutetium nanoparticle. The other peak here is assigned to lutetium-nitrogen bond, which is formed between lutetium nanoparticle and nitrogen in the support. So we observed a lutetium-nitrogen bond between the particle and the support for the highly active catalyst, lutetium calcium 2NH. So we call it anchoring bond. These lutetium-nitrogen anchoring bonds work to anchor lutetium nanoparticle to the spot. And the bond work to prevent the particle from aggregating or from growing. And also it can maintain the high activity of amino synthesis for a long time. And also we see two TEM images here. This is highly active one, and this is less active one. The highly active one shows sharp distribution here, which means they are not aggregated, while less active one shows broad distribution with tail. It means they were aggregated a bit. So we believe that this anchoring bond work to fix the lutetium nanoparticle to the support stably. Okay, I'd like to summarize my talk with my slides. We have 6 hard-X lasers beamline at photon faculty, and each beamline is characterized for somewhat specialized measurements. For example, beamline 9A, we have high flux, and also soft or tender X region are available. So we can measure lighter elements like sulfur, phosphor, and calcium. And at, for example, beamline 9C and NW10A, they are installed in for the equipment for in situ measurements. So in situ those measurements can be easily performed at beamline 9C and NW10A. And also in NW10A, we can measure up to 40 or 42 keV, so we can measure cerium KH. And I'd like to say we will welcome all of you to DAS beamline at Photon Factory. Thank you for your attention.
Overview of work, questions? Okay, any questions? You can reference here. Prasad, I have a question. See, you have energy range from 2.1 to 42. I mean, at a different beam lines. That's what my understanding.
Yeah.
So, and also you mentioned in situ measurements, and you explained that in one example, the right? But one of the problems that we have faced, particularly, I mean, in situ measurements, the low energy, the energy metals. I mean, so the resolution, the quality of the data may not be good as a high energy range metal species, right? High energy absorption range.
No.
Especially
For high
if
energy
you are
measurement,
working, especially we are working in fuel cells, say for example, it's in the liquid media, the electrodes are actually in electrolyte.
Okay, you're working what?
Fuel cells, say for example, or water splitting, electrochemical media.
For higher energy, we use silicon-free 111 crystals.
Okay.
And for lower energy, we use silicon 111 crystal. So resolution is not really bad. It's nice.
Low energy, how you, I mean, standardize the cell for the low energy species, because the absorption length can be shorter for the low energy species, right?
I mean the calculation of the energy?
Absorption length through the liquid media can be.
Liquid media. Maybe we need to make some special style for liquid sample.
Yes.
Yeah.
Okay.
Yeah. But we can try.
Okay. Okay. One question. The question is, what is the procedure to approach exhaust beamline?
I'm sorry, it's a little bit feedback.
What is the procedure to approach exhaust beamline?
Okay. So it's open to everyone, every academic user. So you can apply via our proposal system. And also you can, of course, you can write a proposal in English. So you can contact Professor maybe Kumai or me to handle. I can guide you to how to apply to the DST beamline. So feel free to contact me by email or.
Thank you. Thank you. So once again, thank you very much for the nice talk. So we will move to the next speaker, Professor Mrinmay.
Thank you very much.
Thank you. So Mrinmay Mukhopadhyay. So he is the man and mission who did all the work in that beamline. I don't have to introduce much. Mrinmay, please.
Yeah. Thank you, Sebastian. Thank you, everybody. Thanks for, yeah. Now you can see probably, right? Yes. So thanks. I'd like to thank JNCASR for giving me this opportunity, because though I am involved in this project, but anyway, this formal talk is a routine and it's a part of meeting program. So what I like to talk about is about our liquid surface scattering facility that we are working on for a couple of years, but probably some of you have applied but didn't get the beam time. And so I like to share the status of that beamline and the results from that scattering facility, so that you can get the glimpse of what you can do and what you cannot do in this beamline. Because ultimately you have to remember one thing, that this beamline is designed for all the facilities, including diffraction, reflectivity, and also SAGs. So changing over from different techniques to liquid surface is a time consuming, and that's why we generally try to put all the liquid proposals in one single shot in a year and then try to finish it. And I hope after we reopen this for the general users, we can continue this process for the other users. So so this is a picture that basically I showed several times before, that you can do liquid surface from this. So liquid surface is on. So So you can spread your sample on Langmuir trough, which is basically on a anti-vibration table. So little bit of noise from machine movement or motor movement will not affect. And then we have a, I can go to the next slides. Okay, so this slide. Then we can have a set of slits to reduce the background, and then we have a detector where you can also mount two-dimensional detector. So we can simultaneously do GSAX from liquid and also reflectivity GID from the liquid surface. Okay, so these are the things you can do in our beamline. And then I like to share these slides once because a lot of time we get this type of questions that what I like to use 20-25 kV or some kind of this thing. But if you see this flux versus energy curve, which is something I plotted from 10 to 22, you will see that the peak intensity of the beam line will be around 12. So this is kind of critical energy of our beam line. So, and that's why we mostly do experiment around this region, 10 to 12 region. And this also helps us to do better efficient use of better efficiency of the detector and also the intensity. So if you do experiment around this region, so basically from 10 to something around 14, your intensity is likely to be double than if you do somewhere here. So one case is the intensity is going down because of the photon flux. Another case is the efficiency of the detector goes down as you go higher. But the problem with the liquid surface, we cannot do this experiment here because the goniometer has to move little farther. I will explain that. But if you do somewhere liquid surface around 14 to 16 keV, it is the ideal experiment for this kind of setup. So this is the schematic, and then there is a germanium crystal. So how do we bend? Because liquid surface cannot be bent. So how do we bend? We bend the beam. So we bend the beam by a germanium crystal, and then if you just check the Bragg conditions and the other calculations, then you will see that as you bend the beam, it moves in a elliptical path like this. So yeah, at some angle, your sample beam position is here, but at some other angle, your beam position is shifted. So you have to have a rotation of your whole goniometer to have the beam always at the same position of the sample. So that's why we have a very complicated geometry, but ultimately it works, and I am going to present you some data that it works really good. So this is a trough schematic. So this is the first experiment that we did and published in 2018, that we have a gadolinium in the subphase, gadolinium arachidate, and then we spreaded stearic acid on top of this water surface. So basically it's a gadolinium stearate, which we are working for quite a long time. And then you can see the isotherm. So you compress the barriers and measure the surface pressure with this balance. And then you can see that these isotherms and then what we did, we picked some pressure like pi is equal to 5, pi is equal to 30, and pi is equal to 40. And then we measured the reflectivity at those surface pressure. So this is the reflectivity that we measured. This is the beamline data, so that we collected from the Indian beamline at Photon Factory. So you can see that 5, 20, 30, and then collapse phase, which is basically 40 millimeter. And we also can feed the data very nicely. So you can see that as you go up in pressure, your gadolinium layer, that density goes up, and then the films become more and more less tilted. Like if you see that 5, it is tilt angle is 23 degree, whereas if you go some higher pressure, 22 or 16, it is becoming less tilted. but generally it keeps this gadolinium and stearic acid. This part is the stearic acid and this part is the gadolinium. And then we keep on doing this thing. This thing was not done with in our beamline, but I'll show some GID data that we have done in our beamline. So we have done the GID. From that, we can see that the in-plane separations between the gadolinium ions, and then we can calculate how this gadolinium lattice is forming in the monolayer. And then we can talk. We did some other experiment, like we lifted this thing on some solid substrate. But what I like to say here that the gadolinium is a, we are working on this thing for two-dimensional magnetism. So we had a confusion that what the valency are being used for the magnetic moment. And then we always found that there is a two-tail configuration in the LV field. And the third valency is a kind of free. So what is that valency now? What is it the during transfer or is it in the monolayer? So this kind of information we studied, and then we found out that in the monolayer itself, the valence, the two stearic acid tails are attached to these gadolinium ions, and the third basically it's a hydroxyl ion, and that actually contributing in the magnetic moment in the two-dimensional magnetism that we studied before. So next is the GID that we did one experiment with Professor Joydeep Basu of IISc, and then we he had a sample of DPPC with some quantum dots, and then we added this DPPC and we see nice diffraction peak. So this is basically the grazing incidence diffraction that people always look for, and once you get a grazing incidence diffraction, you can say that the deep beamline is working fine. So far in that during gadolinium stearite experiment, we didn't had this GID, but after this we tuned the beamline and then we got this GID, and now we are trying to improve this even further. So next I have what is my title, that the ordering of JNCASR nanorods on water surface. So these are samples from Professor Somabroto Acharya of ISCS, and then we spread it. We did this experiment together in Photon Factory, and then basically Santanu Maiti, who was our ex-student, who took lead role in doing these experiments, and then we. You can see that the JNCASR rods on a TEM substrate. So basically these are well separated rods of something like 2 nanometer in core size, and then this is a ODA. It's a kind of a polymer encapsulated, and then you have a separation of this thing. So we did some initial experiment like isotherm studies, and then of this Langmuir monolayer of JNCASR. And then what we have observed that if you increase the temperature, so when you have a 22 degrees centigrade temperature, the isotherm doesn't change much up to 40 degrees centigrade, but when you increase it to 48 degrees centigrade, it changes a lot. And we like to see that how that is affecting actually happening in the monolayer, and then we like to continue these experiments, like as we have a heating bath in the beamline. So we did experiment at 22, 30, 40, and 48. So this kind of experiment we did, and then the similar experiment. There is another thing we did here. We can change the incident angle to below the critical angle and above the critical angle. So the way we wanted to prove that one is the surface sensitive. So below the critical angle, you basically get the scattering from the surface, and when you go above the critical angle, you basically probe somewhere between the inside, which is deep inside the water surface. So not very deep, but basically you are close to the molecules which are immersed in the subphase of the water. And then this is the reflectivity we got from so as you can see that this is at 2 different pressure. This is at basically 15 millinewton and 25 millinewton surface pressure, and you can see the goodness of fitting by plotting R by RF, because here you don't see much oscillations, but if you plot it R by RF, where RF is the water Fresnel's reflectivity, then you can see that goodness of fitting, and then you can say that okay, my model is correct. So what we have found that we have a bilayer configuration, and this bilayer configuration is like a corrugated tin. So one is at the bottom layer, another is in between this top, bottom, in between two molecules of the bottom layer. So this kind of a structure we have found, and the tail, which is sorry.
1 minute.
Okay. So, yeah. So basically, you have a ZNS rods, and then you have this tail is a hydrophobic part. So as it is doesn't like water, so basically it moves away, and then you have this kind of arrangement on the water surface. But if you increase the temperature, then you get this bilayer structure doubled. So basically, you have this corrugated tin on top of another, and then you can. We did this thing with let's say we put more material on the surface, and then we see that there is another layer. But if you go for high temperature, so basically this is the same state structure what we got for the low layer. So this bilayer structure is kind of uniform structure structure that we found in the experiment. And then we did the GSAX assessment that I was talking about, that you can do simultaneously reflectivity and GSAX because we have a big detector at the end. And then we can see that there is a two-dimensional ordering of this rod-like feature here, which you are seeing here. Those who know very well GSAX, that these rods I see are basically signature of two-dimensional ordering. And we also did this for basically this is for 0.08 and this is for 0.8. And then we model one of our student Gorango Manna, he basically modeled this and then fitted. So these are the experimental data, and these are the basically generated with this model. So this kind of a pile-up structure is forming at very high pressure. So these are all very high pressure, higher molecular weight. And then you also can feed this experiment, feed this profile so that you can see that how good your model is working with this thing. So with this, I like to conclude my talk, and definitely Professor Sanyal is always the mentor of this beamline, and he is the conceptual design, this kind of rotating arrangement of the reflectivity for liquid surface. Then Professor Somabruta Acharya, Joydeep Basu, and these are the three students. Orpon has worked really hard for this beamline for liquid surface, and these are the three students who worked really hard for this beamline. Thank you.
Questions?
Hello.
Hello.
Hello, this is John Kumar Paul. Hello, Vinrada.
Yeah, sure.
I have just two small questions. Yeah, when you are increasing the temperature, the isotherms curves are becoming steeper.
Yes.
Is it the case?
Yeah, it's because of when you are, as you can see in my this reflectivity and GSAX profile. So it's basically forming double bilayer. So when you have a double bilayer thing, then you will have a less compressible film on the wall.
And another thing, when you change the temperature, actually changing the surface tension of it is the surface pressure. So how do you separate out the fact?
No,
change in surface tension
there is
itself.
no way you can do that because this is true, but we have a surface sensor. So basically it's with respect to room temperature, and this calibration is respect to room temperature and that water surface tension. So definitely we cannot do those kind of things. Yeah.
Thank you, Minwada. Thanks.
Thank you. So at the interest of time, so we won't take any more questions. So if anybody is having questions, please talk to Mrunmayee. Thanks again, Mrunmayee, for a nice talk.
Thanks.
Yeah. So next speaker is Professor Ranjini Vishwanathan, my colleague in JNCASR. Unfortunately, she is not in a position to give the talk, and her senior student, Pradeep, is giving the talk. Pradeep, 13 minutes.
Good morning, everyone. This is Pradeep Kera. I'm working in Quantum Dot Lab JNCASR. So I'm going to talk about our recent work on XAFs in Petra beamline and XRD results from KEK. I'm going to talk about all these results on behalf of my research supervisor, Professor Ranjini Vishnatha. I would like to thank all the organizers for giving this opportunity to share our recent results. So before going to the details, first I would like to thank my research supervisor for giving this opportunity and my lab mate. So we'll be presenting some of the work which is done by us and my lab mate Saptarshi. And I would like to thank Professor Sienna Rao for the generous support and funding from DST, JNC and SSL. And a few of the work which will be discussed here with the help of collaborators from Petra, Professor Wolfgang and Dr. Muzin, and also Professor Chandravas from JNCASR. So the XRF results are from beamline P64 Petra and the low temperature XRDs from beamline 18B KEK with the funding from DST. So these are the recent papers published from Petra, and few manuscripts from KEK results are also under preparation. Majorly, I'll be talking about the last two mentioned work here. So as we all know, recently perovskite nanocrystals have attracted a lot of attention in the field of optoelectronics because of their excellent optical properties. However, it comes with several challenges. Majorly, when you make a light emitting device out of perovskite nanocrystals, due to the continuous exposure to ambient conditions and light, there is chances of phase segregation and device degradation. And also due to the mixed halide perovskites anion migration, there are several challenges when you come to an optoelectronic device. So these understanding the internal structure of perovskite nanocrystals are essential to tackle these challenges majorly. So how does internal structure analysis provides several unanswered questions? So here is one example where we have taken a magnetic Fe3O4 quantum dot and a non-magnetic CDS shell, and we have seen an exchange bias like properties in the magnetic property studies. However, an exchange bias like properties occurring only when there is a ferromagnetic and antiferromagnetic layer. But CDS being a non-magnetic material, the exchange bias properties are unexpected here. So studying the XAFs of these core shell quantum dots, we have seen that there is an FES layer which is at the interface of the core and shell is forming, which is the reason why we have an exchange bias. So even so that is the importance of studying the internal structure, especially at the core shell interface, to understand their excellent properties. So XAFs has been used as a tool to understand these properties here. So we have taken mixed halide perovskite nanocrystals ranging from cesium lead chloride to cesium lead bromide, where the mixed halide compositions are taken, which is following the mixed halide perovskites follow Vegard's law in the mixed halide structure. And looking at the exchange data, and if you look at it closely, we see that there are isobestic points which clearly shows that so isobestic points in these exchange data shows that there are only two paths, which is PBCl and PBBr in the mixed halide perovskites, and the linear combination fit done on this exchange data for this mixed halide shows the actual composition of the halides, and there are no phase segregation or anion migration present in this in these structures. Now, this lead edge data of this XAFs is fitted to understand their local structure. So the K-space oscillation from this XAFs data, it is clear that from a pure chloride nature to a pure bromide nature, the features are shifting from a pure chloride to pure bromide, showing that the homogeneous mixing of near neighbor environment is present. And the lead edge data for one of the mixed halide perovskite shows that there are either PBCl path or PBBr path, and there is no degradation in these perovskite nanocrystals, and the bond length are not altered when you have a mixed halide structure. Now, a similar XAFs fit is done for all the mixed halide perovskite nanocrystals ranging from pure chloride to pure bromide, and the local environment around lead shifts from this chloride rich to bromide rich character periodically, wherein you know that the perovskite nanocrystals which are chloride rich have a chance of defect states being present. So that's why the coordination number is lesser. And as when we increase the bromide incorporation in these perovskite nanocrystals, the coordination number gets better, and the value goes closer to 6. And now that we have seen the local structure around lead in perovskite nanocrystals, it is also important to study how well their mixing of halides are and how the locally how these lead halide octahedras are arranged. So it can be looked at from various length scale, wherein XRD provides from a unit length from a unit cell layer, and XAFS gives you from a local perspective, from a bond length perspective. But however, the mixing of this mixed halide cannot be understood with these two techniques. So we have used Raman spectra as a tool to understand this mixed halide perovskites. So at room temperature, the peaks are broad and we cannot assign their lead halide modes clearly. So and also at room temperature, due to thermal effects and laser induced anion migration, it can give rise to several other issues. So we have taken the Raman spectra at lower temperatures. But before going to low temperatures, we have to make sure that there is no structural transformation or segregation that is happening at lower temperatures. So to understand that, we have done low temperature XRD at KEK for all the mixed halide perovskites, and it shows that there are no phase transformation at low temperatures. Looking at the Raman spectra for pure chloride and pure bromide at low temperatures, now the peaks are not broad and well-defined lead halide octahedral modes can be assigned. And in addition to that, we see a cesium motion peak which is shifting depending on whether the perovskite is chloride rich or bromide rich. So with this, we can actually understand this how well the octahedras are mixing. So coming to the mixed halides, wherever the mixed halides are chloride rich, you see that the features are very close to the pure ones. However, when there is a good amount of mixing in this, the peaks are broad, suggesting the homogeneous mixed halide variants even at very low temperature, which confirms that there are no islands or domains of pure halides which is phase segregated, wherein the mixtures are a solid solution behavior, which is a combination of several possible mixed halide octahedras present, which confirms that the perovskites are very stable in the mixed halide state. And also looking at the cesium motion mode in this mixed halides, it shows a linear behavior changing from pure chloride to pure bromide nature, as we have seen from XAFS as well. However, because of this mixing, and also we know that the octahedras are highly dynamic, a small external trigger like external light, laser, ambient conditions can induce this tilting this octahedra, giving rise to phase transformation from cubic to orthorhombic, which is optically active. So a small external trigger is sufficient to change this internal structure of these perovskites. So with this, we have actually understood the structural aspects of perovskites, which is very essential to stabilize these perovskites from various length scale, from XRDs, XAFS from local structure analysis, and also Raman to understand the homogeneous mixed perovskite nanocrystals. In addition to this, it is also important to understand the interface of colloidal nanocrystals to understand their excellent optical properties. So we have prepared excellent light emitting devices from our lab, but understanding of the smooth interface in this is very important. If you have a graded layer, then the auger recombinations are reduced and the device performance gets better. So it is also important to study their internal structure, but it is very difficult and challenging to study it from TEM. So internal structure through XAFS is very important to understand. So here we have taken pure CDSE core, where the major path is CDSE path. Upon growing shells over CDSE, you can see that the CDS nature increases and the CDSE path comes down. And we know that the coordination number for CDSE or CDS is close to 4. But as we have more and more shell, due to the clustering that we have and clear interface between core and shell, the coordination number goes above 4 and shows the values of very high because they are double counted. Upon increasing these shells further higher, going up to 10 or 16 shells, we see that we have a graded structure, and that is very essential to design very good light emitting devices. So here we see a total coordination number more than 6. It's because that CDS and CDSE, CDS layers are clustered. So the clustering can be understood through XAFS clearly in this. So XAFs as a tool is very important to understand the clustering in nanocrystals, which is very essential to design very efficient optoelectronic devices. So with this, I'd like to thank you all for your kind attention.
Questions? Pradeep, I have one question. Your mixed system, so you say that there is no notable difference in the XAFs data, right?
Yeah.
But if you take chlorine, bromine, there is electronegativity difference also there, right? That can induce a fraction of charge transfer within the system. Can we find, there is a shift in the absorption edge of XANES data? Forget about XAFs.
Yes, so if you look at the XANES data, we see that at the near edge, when there is an edge increase, you don't see much difference. But after you go further, you see this features changing.
Or even white line intensity also, there you can see some.
Yes, even in the XAFs, you can see a transformation from a pure chloride to pure bromide, where the features are clearly different, and you can differentiate that very well.
So you can quantify.
Yes, we can. Yeah, do that.
All right. Okay. So if there are no more questions, so once again we thank Pradeep for a nice talk. So thank you very much. Next speaker is Professor Kaustubh Triolkar from Goa University. So he's going to talk about a defect-induced ground state in magnetic marstenites. Professor.
Thank you, Sebastian, and thank you, JNC, for this invitation. I hope it is the slides are visible.
Yes, please make it in full screen.
Yeah, I'm doing. Yeah, it's fine now. Yeah.
Yes, perfect.
So I'm going to talk about defect-induced ground states in magnetic martensites. All this work has been possible because of this excellent arrangement at KEK as well as through DESY at Petra. And I would like to thank Mrunmoy and Chandrabas for all the cooperation over the several beam times that we have been able to use there. And of course, to Professor Milan Sanyal for the encouragement over the years. So this work that I'm going to present is part of PhD thesis of my student, Rukma. And the main motivation of this work is the strain glass phase that was observed in nickel titanium, in nickel-rich nickel titanium, above a critical concentration of about 1.3% by Xiaobing-Ren's group in NIMS, Japan. So basically, strain glass is a random distribution of static local lattice strains or martensitic nanodomains, as you can see here. Let me get the pointer. Yeah, so, and these domains, the orientation in these domains freeze below a characteristic transition temperature, which is called as the glass transition temperature. And so the ground state is basically a frozen disordered state. So we wanted to understand the defect phases that leads to this ground state, and also look at whether this strain glass is there in Heusler martensites. So because there are many examples wherein impurity doped Heuslers, which are martensitic Heuslers, where the martensitic transition gets suppressed. So for the present talk, I'm going to focus on the iron-doped nickel-manganese indium alloys, which in literature, you can see that there is a strong suppression of martensitic transition with a small iron doping. So we have chosen nickel to manganese indium with this stoichiometry, which is martensitic at around with 400 Kelvin transition temperature. And we have doped or we have tried to dope iron at two possible sites, be it for manganese, that means it will go at the Y or the Z site of X2YZ Heusler. And for nickel, that means we expect it to go to X site in this same Heusler structure. Okay, so what should we observe if it is a strain glass? If it is a strain glass, then there should not be a structural transition. The structure should remain cubic, austenitic structure. The features in resistivity or all physical properties should broaden out. The hysteresis should disappear. There should be a frequency dependence which will go as per the Vogel-Fulcher law. And of course, there should be a non-ergodic behavior in the field-cooled and the zero field-cooled cycles. So this is the parent compound, and it is martensitic. As you can see, it's an antiferromagnet, and the structure is 7M modulated structure. When we dope iron at manganese site, you can see that the martensitic transition temperature decreases, and with X is equal to 0.1, the martensitic transition completely disappears, and you can see that the properties also start broadening out. The hysteresis low. And of course, you can also see that there is a Vogel-Fulcher dependence for this frequency dependence of the storage modulus. So that means it is a strain glass. You can see that there is the magnetism becomes slightly unusual in the sense that there is a magnetic compensation and magnetization reversal below about 100 Kelvin. So there is some interaction between the defect or the impurity that has formed and the main phase. So that was the motivation. So when we looked at the structure, these are lab XRDs at room temperature, and I must mention that the glass transition temperature is around 350 Kelvin. So you expect that the structure of this X is equal to 0.1 to be cubic, because it should be remaining invariant across the transition, but it was the same as the parent compound. So it's something like an unusual strain glassy phase is what we called it. When we go to the next series of alloys where iron is replacing nickel, you see that at about X is equal to 0.2, the structure remains invariant. It remains cubic. There is some small impurity, probably a martensitic impurity, but largely the structure is cubic. So is this a strain glass? That questions can be answered by looking at the properties. We see some unusual DSC. We really don't understand what is causing that, or we didn't understand much about this. But the properties are very sharp. So it doesn't look like that there is any strain glassy transition. Also, the frequency dependence also confirms there is absolutely no Vogel-Fulcher type of dependence. And magnetically, this X is equal to 0.2 with nickel Fe alloy becomes ferromagnet. Okay, so there is ferromagnetism that is induced by Fe. So that's where we wanted to understand the structure in detail as a function of temperature at higher temperature, and that's where we visited BL18B. And we did this experiments at around 15-16 keV. As you can see, this is for the manganese Fe alloy. The room temperature structure is modulated. But when you go to higher temperature, about around 500 K, it's about above 400 K that you see this transition, it was perfectly cubic. So that means there are martensitic domains. They are not nano domains, they are large domains which transform from martensitic structure to austenitic structure at high temperature. So we can look at this structure a little bit more closely, and as you can see that at 500 K, you can see a small impurity phase that you can see here. Now, perhaps this was there even at room temperature, but it was not visible in this cluster of peaks, but you could actually see this at 500 K. And so what was this impurity phase is one question that we had. And when you go on to the nickel Fe side, you can see that the structure in what was obtained from the lab XRD was reproduced with small martensitic impurity. And at 500 K, this martensitic impurity also disappears. That means it transforms to austenite, and the austenitic peak is within this, the main peak of the major phase. So to understand this impurity phase in the MNFE, we also recorded at little higher iron concentration, that is iron 0.2. And you can see that the impurity phase now actually grows. So you can say that this impurity phase is either induced by Fe or it consists of iron. Okay, so because the nickel, manganese, indium all have similar scattering factors as when you come to X-rays, we couldn't actually identify the composition of that impurity phase, but we did EXAFS at P65 at nickel, manganese, and iron KH. And what we see is that in case of MnFe, the iron local structure is completely different from that of the Heusler local structure. It is actually like that you expect for an FCC system. So it is so the impurity phase was actually a gamma phase, and we could say that it is of iron and nickel gamma phase because we knew that there is no indium in this along with iron. So that was, we checked that part. So it could be iron nickel, and iron nickel has a, in the phase diagram, has a large region where gamma phases are formed. So this, we thought that it would be a gamma phase. In the case of nickel Fe, what we saw is that the local structure of iron, now iron is supposed to replace nickel at the X site. So if it replaces nickel at X site, then it should have indium neighbor at around 2.6 angstroms. But what we could find is that the Fe indium bond distance was around 2.9 angstroms, which is similar to the manganese indium bond distance. So that means Fe essentially, instead of going at X site, it is trying to go at the Y or the Z sites, at the manganese sites, and pushing manganese to maintain the Heusler structure. It tries to push manganese at X sites. Now, if that happens, then there should be an A2 type structural disorder, and that A2 type structural disorder can be seen here. The 200 peak essentially vanishes in the nickel Fe, which is there in the MnFe structure. So what we concluded from this work was that if the impurity that you dope or in the Heusler, if it segregates as a point defect, then you have a strain glass ground state. There's a possibility of having a strain glass ground state. But if that impurity is accommodated with an anti-site defect or an anti-site disorder, then you may end up with a ferromagnetic ground state. So that is the conclusion, that strain glass state is not the only impurity doped ground state possible, but at least in Heuslers, you could have either a strain glass or a ferromagnetic ground state because of two different types of defects that get created either within the structure or external to the structure. So thank you very much for the travel support, and these are my collaborators, and thank you.
Thank you, Professor, for a nice talk. Questions? Okay, so any questions from the hall, audience? Yeah, one question.
Sir, this is from JNCASR.
Yeah.
Sir, when you're talking about doping iron at the manganese or nickel site, so both of the iron, sorry, manganese and nickel, both are the ground state is nickel +2 oxidation state, while the iron is for +2 and +3, both are very possible. So did you look with the possibility of oxidation state of iron like +2 or +3 and how they're affecting the structure?
These are metallic alloys. So essentially the valence states of iron, nickel, or manganese are metallic. No, they're zero valence states.
Okay. Okay, thank you.
Okay. If there are no more questions, once again, thank you very much for your nice talk. Okay. All right. So the next speaker, Dr. Savik Chatterjee, UGC DA, Kolkata. Dr. Chatterjee, please.
Visible? My still, sir? Hello, I am.
Yeah. Yes.
Yes.
Make it a full screen, please.
Yeah.
Sir,
Thank you.
A very good morning to all of you. First of all, organizing this user meeting and inviting presentation. During this presentation, I am mainly going to talk about antiferromagnetic Hoyzler compound of composition PD2MnIn. Okay, during the during this talk, during the course talk, first I will give a brief introduction about the Hoyzler alloys and I will show you some examples of Hoyzler based alloys, and then I will discuss the properties of PD2MnIn, those structural, magnetic, electronic, and thermal properties. The structural properties studied at Photon Factory, KEK, Japan, and followed by remarks. As Hoyzler intermittent nominal compositions X2, Y, Z, where X and Y are transition metals and Z is non-magnetic element, and typical examples of these alloys are copper, nickel to manganese gallium, nickel to manganese tin, etc. These Hoyzler alloys is mainly a popular alloy for magnetic memory applications, as previous speakers are already informed some of the alloys of this Hoyzler family. These Hoyzler alloys mainly 2-1 structure, which is a cubic one, but there are certain cases where disorder structures are observed, which is B2, and this type of disordered structure are mainly originated from the random site occupancy of X, Y, and Z. The heat treatment that is given during the plays the behind the observation of such disordered states. So this PD2MnZ, where Z is tin or antimony, this family is actually important for its diverse magnetic structures. PD2Mn and tin and indium-based alloys are actually they ordered in L2-1 structure, irrespective heat treatment that has been given to these samples. And on the other hand, the indium counterpart is very dependent on this on the heat treatment that has been given. Depending on the heat treatment, it may crystallizes in L2-1 or in B2 phase. And the tin and indium counter antiferromagnetic in nature, and as PD2MnIn is antiferromagnetic, number of alloys of this Hoyzler family are antiferromagnetic, and basically for the Hoyzler composition that shows the off-stoichiometric Hoyzler composition that shows shape memory alloys, antiferromagnetic interaction between the original Mn and the doped Mn in Z's site is playing the important role for the observation of shape memory effect or Martin-Selick transition. So it is important to investigate this antiferromagnetic PD2MnIn alloy. So as I mentioned, we mainly focus on the structural, magnetic, and electric and thermal properties of these alloys. These alloys are prepared by arc melting And as the thermal treatment is important for this alloy, we actually annealed this sample at 800 degrees Celsius 24 hours and followed a slow cooling process for 36 hours back to room temperature. So these are the diffraction data that we have recorded at KEK, Japan, and we observed a very good spectrum at room temperature as well as at the low temperature. And as you can see, these alloys are actually cubic throughout the range of the temperature. Structural transition has been observed. But importantly, the 111 superlattice peak, that is the signature L21 phase, we have observed a definite signature of that, but at the same time the peak is diffuse in nature, which indicates that it is totally not L21 structure, but it comprises of both L21 and B2 phase. And with decrease in temperature, we observe a systematic in the lattice parameter of the sample. Around 120 Kelvin, and it indicates that there's depending on the structure of the sample, that is L2 or B2. For ordered L2 structure, the transition temperature is found to be around 148 Kelvin. But for if the sample is ordered in B2 phase, the transition comes around 60 Kelvin or so. So in our case, we observed around 120 Kelvin, which also indicates the fact that this alloy is in a mixed phase of L21 and B2 phase. And with increasing magnetic field, this antiferromagnetic transition temperature shifted towards the lower temperature. And for 9 Tesla of field, the transition is around found to be at 80 Kelvin. With further increase in temperature, no such antiferromagnetic transition temperature has been which indicates that there may be some field-induced ferromagnetic-like state in the material. Isothermal magnetization data indicates that there is definitely a field-induced transition, which is metamagnetic in nature, and actually the problem here is that the pentamagnetic transition that is observed is not a very sharp one, and after the transition also the image doesn't saturate, which indicates that state is not actually pure ferromagnetic one, but we actually got a canted antiferromagnetic state with increasing magnetic field. And with increasing temperature, this the tendency of this metamagnetic transition actually vanishes, and a paramagnetic region is observed above 120 Kelvin. We also checked the effect of hydrostatic pressure and observed that the effect is very similar to that of the magnetic field, and a monotonic decrease in the transition temperature has been observed, about 7 Kelvin 7 Kelvin decrease with the application of 9 kilobar of external pressure we have noticed. Similar in the electrical transport study, we observed the signature of antiferromagnetic transition. But here the important point is that at the low temperature region, the R resistivity follows this with linearly with T square, which indicates that there exists some spin fluctuation in the system. And this R versus MR versus H data also we observed some field induced transition around the 6 Tesla, which is similar to that of the M versus H curves. In case of heat capacity, we observed TQ behavior at the low temperature, which is indication of the fact that this is in the antiferromagnetic ground state, and above the antiferromagnetic transition temperature, it is almost linear, almost flat with increasing temperature. Some concluding remarks. This PD2Mn alloy is possibly comprised of this L21 and B2 phases, and we observe the spin flop like metamagnetic transition these Heusler alloys. The quadratic T dependence of resistivity indicates the spin flux at the low temperature, and the TQ behavior observed in the indicates the AFM ground state of the alloy. So I would like to thank DST, JNCASR, SINP for this KEK form factory facility at Japan, and Dr. Prabhusaji Pramanik is the NPDF student who worked in this project. I'd like to thank ACRB for this, and thanks.
Thank you, Dr. Chatterjee. Any questions? It is there? Okay. All right. There is a question. How weak should the mechanocrystalline anisotropy be for spin flop to occur? Please comment on this magnitude of anisotropy. Hello?
Hello. That actually it is difficult to comment on the odd anisotropy, but actually we have not calculated the magnitude for this magnitude of the anisotropy.
Okay. Any other questions? Yeah. Another question. Could you tell why there is no heat capacity peak at Tn?
No, there's a small on the antiferromagnetic transition, 120 Kelvin. That is.
So probably, it must be checked. Yeah. Any other question? Asked. Okay, if there are no more questions, once again, thank you very much, Dr. Chatterjee, for the talk. And this is the end of this session. So we have a tea break until 11 o'clock. So please join back at 11 o'clock. See you then. Thank you.
Hi, Ranjini. Can you hear me? You can tell me, I mean, is it visible?
Yes, sir.
Is it full screen visible?
Yes, sir. Yes, sir.
Okay, thank you. I should go back. Come out of the share. Yes. It's fine. Sorry. How are you doing?
I'm fine, sir. How are you?
Fine.
Hello.
Hi. Hello.
Hi, everyone. Hi, everyone. Actually, we did not invite them in Krishna Kumar Menon. He's he's there. And he's there. I mean, that is there, but we could have invited for it. See, I got a very, I mean, today morning I presented, no? I got it from Renmai. It's very good data. So we have to look at the data. Okay.
Nice to see you.
क्या सुंदर हैप्पी टू सी यू
कैसे हैं?
हाँ बढ़िया है
Good to see you.
आफ्टर दिल्ली आई थिंक 1 year almost
I think more than that, I guess.
yeah
That's Kanishko.
ah Kanishka da कनिष्का दा को भी मिला हुआ आई थिंक मतलब पिछली बार हम लोग कहाँ मिला था जापान में उसके बाद पर्सनली नहीं मिला ना
No, we meet in Germany, I think. Petra.
Petra. After Japan, Petra.
अब 1 साल से तो सब बंद है.
हाँ सब कुछ बंद है.
Did you go out somewhere? No, you stayed back. Stayed in
No, like
Bangalore.
I went to my hometown in December, Kolkata.
Oh, Calcutta. Oh, everything is fine at Calcutta. I mean, your
Yeah,
family.
yeah, fine. Everything is fine. Like somehow managed everything.
And the situation Bangalore is okay.
See, okay means like the cases are coming. Yesterday also 500 cases in Bangalore.
और
Not Bangalore, sorry, Karnataka, 500 cases.
overall Karnataka. Okay, then it's
Start?
500.
Yeah. Okay.
Sorry. Welcome back to the second session of second day. So the first talk by Professor Sugadha Rai from IICS. So he's going to talk about the breaking down of atomic spin orbit coupling picture in an apparently isolated pseudo one-dimensional irradiate. Professor Rai, please.
Am I audible and
Yes. Yes.
and visible also?
Both are fine. Perfect.
Both are fine. Okay. So first of all, I should start by thanking not only the organizers of the meeting, but the people who are running this program, putting effort to run this program. Professor Milan Shamyal, Professor Chandravas, Professor Konishko Vishas, Professor Sundareshan, and all the associated people. I think this program has been very useful for our group particularly, and I very warmly want to thank all of them. And I also apologize for making a change in the title to some extent. Initially, I gave a title and I thought that I will be talking about one system and give all the detail about that. And then later I thought that because it is related to facility and how it is used, a meeting is based on that.
So sorry for the interruption. So your so sound is actually there is a lack of clarity. So probably microphone or close to the computer.
Is it better now?
Better.
Not very good, is it?
Yes, I mean I can hear it. Yes. Probably please continue and see.
Okay. So I have decided to rather speak on MUS studies that have been carried out at ISIS. I think there is a lot of
Yes.
People have to mute. The MUSR studies have been carried out at ISIS and using the Indian axis. And we have done it on several iridium-based systems. So I thought of briefly touching upon all of them and try to show how these facilities have helped us to do our work. And this work is particularly done by two students, Dr. Abhishek Nag, who is right now working in Diamond as a postdoc, and then Dr. Abhishek Bandyopadhyay, who is going to join ISA Pune as a RA. And then there is Professor Fabrice Bart from France and Professor Avinash Mahajan from IIT Bombay. They have been instrumental in behind these works. And then two scientists from the ISIS line, Dr. Pavitra Viswas and Dr. Adrian Hillier, they have been extremely helpful. So I acknowledge all of their effort. So the point that we, for last few years, I think 4-5 years, we have been working on iridium-based systems with certain particular interest. Now, it's all known that, I just give a very brief introduction that we all know that a system when it goes from 3D to 4D to 5D, the bandwidth continuously increase, but the correlation, electron-electron correlation strength U continues to decrease from 3D to 4D to 5D. And as basically, I should be taking Just a second. Okay. So as a also the from going from 3D to 4D to 5D, another parameter increases, that is the spin orbit coupling or lambda. However, in the context of magnetism, we had always considered U to be the most important parameter. So what we did was, so because the U is continuously decreasing going from 3D to 5D, so people are not interested about 5D magnetism. But in recent times, the spin orbit coupling has taken a center stage of physics, advancement of physics. So there is a growing interest for the last decade about the 5D systems and their magnetism. And so basically in the periodic table, it's these particular elements, molybdenum, ruthenium, rhodium, tungsten, rhenium, osmium, iridium, they have been considered to be important, and we focused on iridium. And we focused a particular oxidation status on a particular oxidation state of iridium, and that's I'll tell you what is the reason. The story is that the oxidation state of iridium is 5+ that we focused on. That essentially means you have 4 electrons to put it on in 5 or 5D orbitals. So even a school student will be able to put it. So these are the T2G orbitals, 3T2G orbital, 2EG orbitals, and because it's a 5D system, the crystal field splitting is very high, so your EG and T2G are very strongly separated. So your Hund's rule is defied, and 4 electrons you put in this way, and you get in a low speed state. So it's very simple. It has 2 unpaired electrons, so the system will have moment, and it's a partially filled band, so it should be a metal. Surprisingly, none of these systems turned out to be metal. All of them turned out to be insulating, and the moment mostly turned out to be rather small. So people said that this kind of a description, which we within the Hund's rule or within the low spin orbit coupling strength description or the LS coupling description, might be wrong. So let's get into a J kind of a picture. So everything you now express in terms of J. So effective L, considering only T2G, is taken as 1. There are 2 unpaired electrons, so it's equal to 1. So you calculate J is to be 2 plus 1 and 0. So the whole argument then became that if we are having a low lambda limit, then we are working in the LS coupling regime, and the system is magnetic and metallic. Now we increase lambda, going to higher lambda, and then go to JJ coupling limit. Then what is happening is the only levels or the states that are possible are these states, and the lowest energy state in this case is a J equal to 0 state with the MJ is equal to 0. So the system is going to be non-magnetic. So if you are in the LS coupling regime, the system is supposed to be magnetic. If we are in the JJ coupling regime, the system is going to be insulating and non-magnetic. So the question that appeared, all the systems that we work on, whether they are magnetic or non-magnetic, depending on that, we can define that what part of this scale we are sitting in. And because these pictures are all pictures of atomic iridium, these are because spin orbit coupling is an atomic phenomenon, so this picture is drawn from an atom of an iridium. But in reality, we all work with solids. So iridiums are sitting within an octahedra. This octahedra is sitting in a crystal structure with a lot of distortions, different hoppings, different bandwidth. So a lot of other factors coming other than spin orbit coupling. So then we thought that let us check the hypothesis with iridium and iridium-06 octahedra, but in different crystallographic environments. So we started with an environment which looks like this. This is a 6H hexagonal perovskite, and these green octahedra that you can see here making a dimer, these are the 2 IR06 octahedra sharing a phase and basically creating an IR209 dimer. One dimer is here, another dimer is there. So 2 iridiums are very close by and all this thing. So when we did the magnetic measurement, it looked like the magnetic data looked like just like a paramagnet. So you can do a Curie-wise fitting and you get a very low moment of 0.2 Bohr-magnet. It's not exactly 0 but very low. And theta turned out to be rather high, minus 30 Kelvin. Please note that this data is still 2 Kelvin and there is no order. But when you do a Fourier-wise fitting, you get a theta to be minus 30 Kelvin. That's somewhat unusual. So why the nearest neighbor interaction appears to be so strong, but still the magnetic system does not order? So the question is, this system, because the moment is low, this system appears to be very close to J, but it's low, but it's not exactly zero. Try to understand why this moment is coming. I will not get into that here. But the question that came is that when the theta is minus 30 Kelvin, so the nearest neighbor interaction is rather strong, why the system does not order down to 2 Kelvin? How these tiny spins are acting? Do they act like paramagnet, or there is something else which we are not able to see? We have extensively worked on this system and published quite a few papers on these systems. So, but while solving this problem, we went to this particular facility in ISIS, which is MUSR. MUSR is a local magnetic probe where in this curve, the polarization relaxation of the muon particle that we have put it in the solid in the sample. This muon particle polarization is getting relaxed as a function of time at different temperatures, starting from 150 Kelvin here to 100 millikelvin. And what you see is that high temperature ones are like Gaussian, like a very slow relaxing thing. But certainly from these temperatures, there is a relaxation increase, enhancement. So from, let's say, 60 Kelvin onwards, there is a fast relaxation shaping. The first thing to note is that none of this polarization relaxation shows any oscillation or a one-third tail, which is more involved with the MUSR literature. But basic point is that down to 100 millikelvin, these curves tell us that the system does not order, the spins don't freeze down to at least 100 millikelvin, although the theta turned out to be minus 30 Kelvin. So now there is this relaxation coming up at starting from, let's say, 60 Kelvin or so. And then we try to fit this curve, there is one static, forget about these functions, they are not so important. There is a fast relaxing component, a slow relaxing component, so on and so forth. But the basic point is, what we realize is that starting from 60 Kelvin, the muons start to relax fast. That essentially means the spins that it is seeing, the spins are going to starting to correlate with each other. So the spin fluctuation starts to slow down, as you can see from the right side plot. And then from 2 Kelvin, look at this part, the 2 Kelvin plot curve and the 100 millikelvin curve exactly fall on each other. So what is happening is, starting from 30 Kelvin, the spins are no longer like paramagnetic spins. They start to correlate, they start to slow down, but still fluctuating. They continuously slow down, and then at 2 Kelvin, they remain, they don't change. That means they have slowed down, but then they are still fluctuating, and the fluctuation continues like flats down to 100 millikelvin. So the system continues to fluctuate. And this is this fluctuation rate shown. This is the particular fluctuation rate, it continues. That's what MUSR tells us. And then when we went to our theoretician friends, they say that these are, let's say, the Ayatollah and dimers. If you really calculate the J values, these two spins are antiparallel to each other because J is minus. And these two are also supposed to be antiparallel because the J is minus. So the spin orientation should change. But then this one and this one all should be antiparallel, and when this happens, because it's a hexagonal structure, what one gets is frustration. The spins exactly do not know what to do, and what the spins then do is this: the spins continue to fluctuate until they freeze.
Hello?
Yes.
One more minute, please.
So I'll be finished. So that's what we have done. So we must show this. And as I have wanted to quickly go through it. And after this, we have changed the system and tried to take the lithium further apart in a double perovskite system. Green octahedra and iridium quite far apart. When we do that, however, the reason for taking iridium apart, to take it to more atom-like situation, the situation that happened was, if we go to more atom-like situation, the moment should come down because we reach J equal to 0. But the previous system had a moment of 0.2 and this became 0.4. And I'll quickly go through it. And again, we tried to do MUSR, and the MUSR essentially told us that how the system spins are going to correlate with each other at higher temperature, slow down, and then at some point of time, they become flat. This fluctuation rate becomes flat, or the relaxation rate becomes flat. System continues to somehow, these systems never order. The frustration is very high. They continue to fluctuate. And this is the one that I tried to initially thought of telling you. So I'll not really bother you again. This is another attempt where we have tried to separate the iridiums even further. This is pseudo one-dimensional columns. And iridium octahedra, these magenta ones are very separate. So we thought the iridium will be more atom-like, even within the solid, like a separated atom. So the pure spin orbit coupling contribution will be seen. So it will be like a J equal to 0, and that's what we tried to do. Unfortunately, this showed even higher moment. And we have done MUSR. Again, this was fascinating results we had from there. From 30 Kelvin, as high as 30 Kelvin, the spins, fluctuation rate of the spins become flat, absolutely flat. It's a very complex system. I think it will take a lot of time. So I'll end up just showing you that, contrary to our idea, when we separate the iridiums more and more apart, with an assumption that iridiums are separated, so they should be more atom-like, so the spin orbit coupling effect will be more enhanced. So it will, the JJ coupling limit would be more realizable. So the J equal to 0 state should be attained. On the contrary, what we found that when you try to separate the iridiums further, the moment increases, though tiny moments, but they increase instead of they decrease. So we now tend to conclude that this iridium-based system, the spin orbit coupling, is still not that high to call them a JJ coupling system in reality. So I will stop here by thanking the audience, and once again thanking the people who run this program, who had been extremely cooperative with us, and without their help, all this work wouldn't have been possible. Thanks a lot. Thank you very much.
Questions? Yes.
There is a question, what is a stretched exponent?
Yes.
So this is used to, let me go back if I have written. For example, if you look at this, so just a second. So if you look at this particular exponent, this is normal exponent. So the stretched exponent is a power of this, a power beta given on top of this. So if I don't remember whether I have given an expression here. No, not here, but basically it's as you can see, exponential lambda t to the power beta. That's a stretched exponential, which is particularly used to explain how the spins are relaxing. These are not really nuclear dipoles. The spin dipoles, how they are relaxing. In certain cases, these are useful. It's not. In this particular case, for example, it is also a stretched exponential with beta is equal to 1. So when stretched exponential is one where beta is not equal to 1, beta takes certain value. Like for example, in this case, beta was close to 0.8 in this case, and then it fell down. That talks about the magnetic homogeneity of the system.
Okay, at the interest of the time, so let us conclude this talk. Once again, thank you very much, Professor Rai, for this nice talk. Yeah, so we will move to the next speaker, Dr. Sachal Kumar Ghosh from SNU. Dr. Ghosh, please.
So do you see my?
Yes.
Okay.
So yeah.
Is it in full screen now?
Yes.
Okay. Okay. So let me start by thanking to the organizer for this opportunity of showing our work, which is recently came in applied surface science. So I'll talk a little bit about a topic in biophysics, especially in membrane biophysics, where we try to see how this graphene oxide interacts with cellular membrane. I would say a model cellular membrane, and it brings the corresponding structural changes over there. So point is that why are we interested on that? Before that, let me tell you what these biomembranes are. So if you remember your school days, so this was like our picture on left-hand side. You see that this is the cellular, it's a cell, which is the functional unit of any living organism. So that has this, let me see, how can I get the laser pointer? Yes, okay. So this is the cell, and this is the cell membrane, and this is the outer boundary, and it interacts with any external molecule that wants to go inside the cell. So it's a quite complicated 2D structure you see there. So not only that, this play a lot of function for this living organism to be alive. So now you wanted to see that how graphene oxide, I don't need to introduce what is graphene and graphene oxide to this community. You all know what it is. So the point was that how it interacts with that. So why we are interested? So this now becomes very important, especially in biomedical sector. So where people are trying to deliver a targeted drug delivery inside the cellular system. So that's an important carrier. So this graphene-based material, graphene oxide, especially because of these functionalities, lots of there are carboxylic, hydroxylic, and epoxy group that interacts with water. So it becomes easy for graphene oxide-based material to use as a drug delivery vector. And it has been shown that this graphene oxide and graphene also very antibacterial in their nature. So if you put a bacteria on this material, so that bacteria cannot multiply. That means they cannot multiply its more and more. So it stops there. And not only that, recently there are lots of reports where people are trying to use these graphene-based materials as the base of biosensor. So because of this, its electronic structure, so it becomes like a basic of organic field effect transistor and so on. So our point is that wherever you talk about all these, there is an important point that how these graphene-based materials, or I would say small graphene flakes, interact with the first boundary of a cell. This is the cellular membrane. So that controls everything, every functionality. Okay. So that's the point we wanted to understand, and because of that, so we use this photon factory beamline 18B. So this was, I mean, this picture is known to all of you, but the point is here is that if you look at this sample, so this is the multi-layer structure of these biomolecules, which mimics the cellular membrane. So there are lots of stack of such single membranes are there. So there are many membranes are there, and separated by this blue region, which is basically the water, we call under controlled humidity, thin layer of water. And we used XRR and X-ray reflectivity and grazing incidence X-ray diffraction study to see how these molecules are organized in and out of plane, and also when I add this graphene flakes, what it does to this structure. So if you look at this simple black peaks, which comes from this one-dimensional periodicity along this z-axis, if I call it a z-axis, so that gives you, it's like a symmetric liquid crystalline phase. So 1D ordering along z-axis, that will give you lots of black peaks. So after getting these black peaks, what we used, we try to find the electron density corresponding to each each of this membrane, so which will come from the form factor of this membrane. So you have to just do some modeling, considering that what could be the possible form factor, like what could be the possible electron density of individual membrane. From there you calculate the form factor, and ultimately you get the scattering intensity. So these are some of the equations we have used to try to figure out this electron density distribution in a membrane. What interesting is that when we add this graphene flex, what we found is that instead of one set of Bragg peak, which you see when you have the membrane without any graphene flex, but when you add this graphene flex in your sample, which is having a size of around 100 nanometer, you see there are second set of peaks come, which is also provides a lamellar stacking or symmetric liquid crystalline phase, you see, that is induced in the presence of this graphene flex. So what is going on here? So we tried, as I said, to find out the electron density of individual membrane using these simple equations. I mean, of course, there is related MATLAB coding and fitting. There are a couple of things one has to do to figure out this density, electron density. So finally, what you see is that there are two sets of Bragg peaks. What I said, each set follows the one-dimensional periodicity of lamellar stacking. And if you try to figure out the electron density from that, what we found that in one set, which is very close to the lamellar stacking of pure lipid system, like pure system without graphene. And another set, which is very different from the pure lipid system, where you see that this hydrophobic region, if you look at this cartoon here, which actually describes how this membranes looks like in a cartoon. So what I say that in one case, the hydrophobic core, which is here in this blue lines, this hydrophobic core remains intact almost, I would say. And in another case, there is considerable changes, like lots of undulation happens in the electron density, which is there in the hydrocarbon region. So if I look at very carefully, what we see that this set, which is close to the set of pure lipid system, that also has some mainly comes in this regime. So which actually describes my head group region, this pinkish region of the membrane. And this region, if you look at this region, that actually represents this hydrophobic or hydrocarbon regions of the membrane. So in one case, you see there are a lot of change over here in this pinkish region, which is the head group region, which is the polar region of the membrane. And in another case, you see a lot of change in the hydrocarbon region, which is the core of the membrane. So what we figure out that corresponding analysis to this electron density. So it looks like that is few flex is going over there and other few flex are going over there. Now, point is that in a given thermodynamic condition, how do you get these two different kind of structure which is coexisting in the same condition? So what you figure out that I mean, these kind of things were in a recent paper in Nanoletters were predicted by simulation, but we could figure out that yes, it actually happens. But the possible region could be that that we are thinking that this graphene oxide, which is also lots of patchy region, which is purely hydrocarbon, purely carbon. No, so 30% carbon was oxidized, having this COOH group or epoxy group and so on. So these flakes are having some patch which is mainly hydrophobic, which generally will attach to the chain region of the lipid, and where there is oxidized, that region naturally will interact with the polar head group region of the membrane. So you see, when this both the components are taken in a solution, they will make that a very small complex local complex, and over time they will self-assemble on evaporation of the solvent. They will self-assemble the way they have initial complex is. So you do see such kind of two different phases in a given condition, and which is reflected in the Bragg peaks of the lamellar system. So then we figured out that if we think that some sums are going here and sums are going there, then what kind of organization change happens in the plane of the membrane? Okay, so the lipid we choose, that is called DPPC. So this is kind of deuterionic lipid that has this kind of geometry where they have this chain, straight chain, which is frozen chain, sometimes we call it, and they form a two-dimensional hexagonal lattice in the plane. Okay, so that lattice you can follow that what happens to that. So we did this GIXD, and the GIXD clearly shows us that because of the presence of this graphene flakes in this region, that 2D lattice gets distorted, and your corresponding, if you see from this width of this, so the correlation length changes. So you do see a change in the lattice as type as well as its correlation length. And also, this molecules has very interesting feature that makes an angle with that surface normal, which we call the tilt angle. We saw that in the presence of these graphene flakes, this tilt angle also changes. So there is reasonably, we can predict that, or we can conclude these molecules are, these flakes are there in the core region of the membrane. So this was the PF photon factory work, what I showed here. Later on in 2008, like in the same year, we had in Petra 3, where we had the opportunity to do this XRR study and GID study on Langmuir monolayer. What happens in this case, instead of this kind of this here, where you have this stack of bilayers, here you take a single layer of lipids at air-water interface. And then you do the similar study. And if you look at this electron density, I'm not just showing every data, but I just show you the electron density corresponding to the presence of graphene oxide and without graphene oxide. But in this experiment, what we did, we tried to tune the electrostatics of interaction between these graphene flakes and the lipid layer. So this is the electron density in the presence of graphene flakes for a deuterionic lipid.
Can you hear us?
Yes, I can hear you. Maybe those who are not presenting or talking, they may please mute.
No, actually we wanted to say that you have 1 more minute, I guess, right? Yeah.
I am following my stopwatch, okay? Yeah. So if you look at this here, the deuterionic lipid, there is some interaction. You see the change in electron density, but in case of negatively charged lipid, there is no change at the presence of geoflakes. But if you look at this positively charged lipid, you see a tremendous change in the electron density distribution. So we just gave a possible distribution or the arrangement of the flakes like this, this one was also already predicted by our multi-layer experiment, but this too we just propose that it probably is happening because of this electrostatics, that negatively charged lipid does not allow it to go close to the membrane, that because of this this COA minus or OH minus groups which is there in the graphene oxide flakes, but it attracts the positively charged lipids, and they make a layer, they make a layered by layered organization of these graphene flakes below the membrane. So this paper will be submitted soon. This is with Professor Murphy now. So this is like some outcome from the beamline times we got. So we got 7 beam times from in PF since 2015 and 1 in Petra. So we could manage to publish already 7 papers, and 1 is under review and 1 is to be submitted very soon. And these are 2 conference proceeding paper, and these are the students whose PhD work somehow linked to the experiments done in PF and Petra 3. And I really appreciate all the organizers and those who are maintaining these 3 or 4 beam lines in different parts of the world. Thank you so much for taking this pain and extending the opportunity for us to go and do our experiment. Thank you so much.
Thank you very much for a nice talk. Very good publications list. Thank you. Questions? Yes. There is one question.
Okay, so how do I see that? Can you take, so I'm just in presentation mode, so I can't see what, Acha.
Yeah, can you comment on the scope of the study in combination with the magnetic drug delivery?
So if you look at this study, we are mainly interested to the change of the membrane it brings. So we can also, of course, predict that if a particle which is magnetic in nature, if it is going inside the cell or not, or whether it is preferably interacting with the membrane or not. So this kind of experiment could tell you that what is the outcome, whether it prefers to interact, whether it's being delivered inside the cell or not. That can be concluded.
Okay. Okay. Yeah, at the end of the time, so we thank you. So you are nice talk.
Thank you.
Yeah. So the last talk of this session is Dr. Arpan Bhattacharya. So you all know him, and those who use the beamline. So he was taking care of the beamline several years. He knows in and out of all the parts of the beamline. Arpan, please. Arpan, we can't hear you. Hello?
Hello, can you hear me?
Yeah, now we can hear you, but we cannot see your slide.
Can you see?
Yes.
Okay. I'm going to slide here.
Yeah. Please make it a full screen.
Yes, yes. Yeah, can you see?
Yes. Please go ahead.
Okay. So, thank you all the organizers and my PhD guide, Professor Sanyal, and Vinmada, and all other colleagues for this opportunity. It has been a great journey with KEK and Petra being involved in these projects and getting the flavor of such great facilities and working in them. So I could not stop myself from sharing some of the beautiful views that I conjured during my tenure in KEK, Mount Tsukuba and different seasons of the campus itself, and the Sakura season especially, which reminds me of the great beauty Japan has. Now, this is our beamline. I'll just give a brief discussion, not discussion because most of the things has already been told, just a few of the setups that I have worked in and the users that can use the reflectivity and the diffuse scattering setup, the low temperature setup for diffraction. We can also customize it for thin film, high temperature setup both for thin film and for powder diffraction, the small angle X-ray scattering that now can be modifiable for different Q values as well. The liquid setup already extensively discussed by Minmada, and the high pressure setup, which is also available in our beamline in KEK. So, two particular, before starting the small angle scattering, because my topic of my title actually is studying self-assembled systems, and for that we have used this facility particularly. Hello?
Arpan, sorry for the intervenes also.
Yeah.
There is some issue with the sound. I'm not sure whether it is because of the microphone. Kind of an started.
Some background?
Yeah, something.
Okay.
If you are using microphone, maybe you can remove and talk. Comment, that is also fine.
Using microphone, I'm using the mic of the laptop.
Sir, if you're using microphone, please don't put on close to your mouth.
No, I'm not. I'm using the laptop microphone.
Okay. Okay.
But it's not clear.
Some static background is there.
While talking is the problem.
Oh. Am I not audible at all?
It's you are audible. The problem is actually, I mean, it's not a clear voice.
If you have headset, you can try it for once.
The problem.
Can you slightly move away from the laptop slightly? I mean, so.
Yeah. Can you hear me?
Yeah, there is a good comment. Maybe your mobile around there.
Yeah. Yeah. Hello?
Yeah. You can keep your mobile away from your computer.
Yes. It is there. It is not there. The static persist. Hello?
Yeah. Yes.
It is still there?
Same problem. Well, maybe you can reduce the volume a little bit. I mean, I'm not sure how it will help, but you can try.
Maybe the fan of the interfering.
Possible.
Then I have to change computer.
Probably you can continue. We can hear you, but it's not great clarity. That is not our worry.
Oh. That's the problem. Okay, anyway.
Anyway, you continue. Yeah, please continue.
Okay. So this is the fax apparatus which was designed by Professor Sanyal and Mehnada with help of others, and we have a 4-meter long flight tube, and left side is basically the side of the sample, and we can see the detector far behind, which is a Pilatus detector. I will not go into details of scattering, fax theory. Only I will mention that different kind of samples like fibers, colloids, proteins with high length scale can be measured directly through this process. And in this process, I would mention 2 works that we have done where we could modify the sample stages itself for different kind of conditions that were required for experimentation. One is from Professor Ashok Ganguly's group. Vaishali Sethi came here and worked here on colloidal system, and in their system they wanted to study time evolution of liquid phases. So at that time we did ex situ measurements, but now even in situ measurement with liquid sample phase is possible. And another work already I have heard from Professor Fajol, and here we had to modify the detector side because they wanted to do reflectivity and GID simultaneously, and we modified the setup accordingly. So basically, the users who are actually want different conditions and for their measurement, we try our best to arrange it for them so that the best output of the experiment can come. Now I come to my work, which was in collaboration with JNCASR Professor Kulkarni group and Professor Shruti George's group, who synthesized this molecule DMBNCS, methyl biliogen, and chlorine tetracarboxylate potassium salt. Why it is important? It is important because these two actually, have the property of forming charge transfer complex, and after that, it actually rearranges itself under aqueous solution into this kind of 6 nanometer cylindrical micelle. This is a self-assembly process which happens all the time in the nature, and it is, imperative that this kind of controlled self-assembly is possible because it mimics biological systems and things like that. And we wanted to study this system, which further coalesces into 50 to 150 nanometer diameter fibers. And these fibers have unique properties like very high humidity sensitivity, and for that it was also used as humidity sensors. But we wanted to know why it is happening. That's why we made this sample cell where we could use different salt solutions for different humidity conditions and take these kind of stacks images in GZAX condition. This is the incident beam. This is the Pilatus image that we can see. This paper was published in scientific reports in 2017. So I'll just go through the basic findings. What we found for this sample was that basically the ordering is hexagonal in nature of the micelle itself, and with the higher humidity, there is a the distortion in the lattice actually reduced. So the 5% relative humidity, there was a high distortion in the lattice, but with higher humidity, the distortion certainly diminished. So this is the data reduction that we applied, angular cut. We measured the QY and QZ plot of this data, and these are the plots that we found. And we found that there are 3 distinct phases. One is the hexagonal phase, where at higher humidity, of course. Second is the second is the lamellar phase, and third is the normal liquid solution phase. This data was taken during the drying process before we used the sample cell as our reference. And also the shape of the micelle, individual micelle, actually changed during the experimentation. That I will go directly. Here we can see that the experimental data and the simulated data parallelly simulated extracted intensity from the data of the micelle, and we see that with higher relative humidity, the shape of the spot is changing. And from Curie principle, we know that the shape of the change in the shape of the individual elements conjures or is dependent on how we see the individual spots change, and these two are correlated. So we can see there is a elongation during the y-axis for 96% from 5%, and that means that there is an elongation of the individual micelle in the x-axis direction. And this is what basically was concluded. You can see the D1, where we see the individual lattice elements of the fibers. Without water, it has a theta distortion of 45 degrees. That is highly distorted lattice. With higher humidity, that is the highest one. The theta distortion is 59.4. So almost 60 degrees, which is a perfect hexagonal lattice, but there is a elongation of the fibers in the x direction. And that is the, I mean, basically drying data, which I have already mentioned. I will next go to the.
Hello?
Hello?
You have 2 more minutes, please.
2 minutes?
Yeah.
Okay, I'll conclude as fast as possible. Yeah. So now I'll go to the 2D part, because in the solution phase, this kind of fibers self-assemble, we wanted to see, because DMB itself is a, I mean, amphiphilic molecule with hydrophobic head and hydrophilic tail. We can mock this evolution in 2D phase or not. So for that, we did put DMB solution on a LB graph and put the CS into the subphase, and we saw that this kind of films are forming with pressure. This is the Bristol angle data, and we see that at pi equal to 28, that is higher pressure, we see a high and compact film of DMBCS possibly. We didn't know till now. So for that, we wanted, we studied it through, through reflectivity, and we actually from EDP data we concluded that it is indeed DMBCS, and the best possible film that is erect film without any tilt was found at around 30 pressure. And then we wanted to see the internal composition, and for that we employed GID measurement. This was done in Soleil, France, and the GID measurements gave very interesting results actually. I mean, the first was the tail ordering and head ordering of DMB and CS that I'll just explain in the next slide. And what we saw in the first slide was that at very low pressure there is no peak, so there is no ordering at all. At intermediate pressure we saw CS ordering in the diagonal direction, and head ordering, that is the pi-pi bond between DMB and CS with a very strong peak. At very higher pressure we saw that peak, that head ordering is diminished, and tail ordering, that is the amphiphilic, that hydrophobic tail ordered in a hexagonal fashion, on the ordered in a hexagonal fashion in a monolayer, that peak we saw is very, very prominent. So there is some kind of arrangement of molecules going on in the LB graph. So for that, I'll just explain what is going on. So this is basically A shows the phase where CS is in subphase and DMB is normally on the water surface. Then DMB and CS, they actually make the charge order complex and form this kind of linear chain. These linear chain at higher pressure, higher pressure means like 10, around at 10, form this kind of linear, floating structures. And if you see the unit cell is like a rectangle. But at very high pressure, but we see that at this point, the tail ordering is not there, because there is no hexagonal ordering on the water surface. So at very high pressure, what is happening is that there is distortion due to the potassium repulsion, electrostatic repulsion on the heads, and for that the heads are twisted and the head ordering goes away, and the tail ordering is there. And when the pressure is even increased further, what happens? The film collapses, and since it has to, since it is an amphiphilic molecule, what happens is, what happens is, we can see from AFM study, this kind of small nanowire is seen when we take the film out and observe it under AFM. And these are exactly of the same diameter and the same length of the films that of the nanofibers that we that were formed by self-assembly in 52 self-assembling transmission that we are seeing, which is being mimicked under LV trough under pressure. So, in conclusion, this kind of 2D to 3D transition is possible for these kind of amphiphilic molecules, and we need to study further what are the internal exact mechanisms to molecular dynamics maybe. So I'll conclude myself. I'll acknowledge my professor and Professor Kulkarni, Professor Nirmal Mukhopadhyay, Professor Subi George, and Chandra Narayana, under which I worked during my tenure. Umesh, who has been a very valiant contributor, and all my colleagues for this. Thank you so much, and sorry for this faux pas. Basically, I didn't realize the sound quality was coming like this.
All right. Thank you very much, Arpan. Such a nice talk. If anybody has quick question, yeah, there are three. What is? Yeah, one question. Is the liquid diffractometer working now? Yeah. Scattering, for scattering, experiment from air-water interface. Yes, it is working.
Yeah.
It is working. Okay. Any
Hello?
other questions?
Hello, Arpan. Yeah, I am Jayant Paul. I have one question.
Yes, Jayant.
Yeah, the 3D structure is forming due to increase the pressure above collapse pressure.
Yes, above collapse pressure. Yes.
So actually the isotherm you have not presented, so it's very interesting actually to see the isotherm, to see the collapse nature.
Time to completely discuss because if we meet that personally,
Very interesting laser and very delicate experiment. Yeah, thanks. I will contact you later.
Sure. And you see
Okay, so once again, thank you very much, Arpan, for a nice presentation. This is the end of this session. I would like to thank all the speakers. For your kind, time, and then the beautiful work and then presentation. It gives, the the importance of this beamline and how powerful this beamline, so for most of our research activities currently we are using. Many of us probably, may not be knowing actually the depth of, the work we can done with this beamline. So please make use of it, and we have upcoming, proposal for the next May, June times. Please be in touch with us. For anybody who wants to utilize this facility. And I take this opportunity to thank Professor Milan Sanyal, the visionary, for this beamline from the day one, and he still is, very, excited to take it to the next level. Thank you very much. And Mrinmay and Professor Chandrabas, in various technical aspect, for the last 10 years. Arpan and others, took care about this beamline in great shape, and it is our responsibility to take it forward. Thank you for everybody. Work hard and behind. So make it one of the the best facility. So we have at the moment in our hand. Thank you very much. So now it's the lunch break. We will get back into action for the next session at 2:15 p.m. Thank you. 2:15. Yeah. Thank you very much.
Hi, Sean.
Good morning, Roger. How are you?
I'm all right. Good morning.
How is the meeting going?
I think it's going okay. I just woke up around 5:30 and just attended morning. Some talks are very interesting. Yeah.
Ah, good, good.
So you are testing now your presentation.
No, I think that was the reason for just kind of, I got an email from Jai Chandra asking me to just, it seems to work. Well, I don't know, how do you, we try?
Good morning, Son and Adruja Sundaresan.
Good morning, Sundarshan. How are you?
Yeah, good.
Morning.
Everything's going well.
Yeah.
So you can see a big hall and sitting alone. There
Yeah.
are people
Oh, yeah.
outside.
Yeah, the people are attending from the home, isn't it?
Yeah, they will be coming. Yeah.
Oh,
Otherwise, we don't feel that, we are conducting a meeting.
that's right. Yeah. No,
Yeah.
it's good thing. Yeah. There are many interesting talks. Yes.
Yeah, going on. And so Son will be there for half an hour, 30 minutes or so.
Something like that. Yeah, I do apologize, Sundaresan. It's yeah. So I'll come off this call and go into my lecture in France.
Okay.
It's a shame.
Okay.
But I think the talks have been recorded. Is that right?
It will be available in the YouTube, JNCASR YouTube. It will be available.
Yeah, because I know a few people in that who were
Yeah,
unable to
yes.
attend, so that would be great.
So how things are improving now? How is the situation?
So we are nationally still in a lockdown. And yeah, and the statistics are improving. So we appear to have a very successful rollout of the vaccination program.
Okay.
So I think the combination of the vaccine and the lockdown means that the numbers are becoming more positive. So we do have now a sort of timetable from the government as to when they'll start to relax the restrictions.
Okay.
According to their planning, I think it's soon when we expect to be able to remove restrictions. So I guess the government's taking quite a cautious approach because we still have a lot of people in hospital and so on. But it does seem to be slowly improving. At the lab, not a great deal has changed, but we expect that to improve.
What about the experiments are not running now? Absolutely, it is.
So yeah, so we do because of COVID and some other issues. Actually, some of the projects that we wanted to do were going more slowly, in fairness. But now we'll run this new cycle from April onwards. So we'll run the same amount of beam time. It'll just be slightly later in the year, which is a good thing.
Okay.
Would you mind share my screen to see if the presentation?
Yes. Yeah, please. Yeah. Somebody is doing. What is he doing? Ask who is doing.
No. Oops. Can you see that? Does that work?
Yes.
Okay, great.
Okay, so I'll try my one.
Whoops, sorry. Let me try and get out of that, Roger. Stop sharing.
Can I try mine?
Yes, please try. Yeah.
Let me just put on and share the screen. Can Can you see it now?
Yes.
Okay.
Yeah.
So
Yeah.
that, yeah, that's good.
Yeah.
Okay. Okay. Thanks very much. Yes, I'll stop now.
Okay.
Stop. When you stop, stop. Yeah.
Emma, the program you have print. Print. Oh. Dr. Lala is also there. Maybe he wants to check his connection slide. Dr. Lala, good afternoon. You have to unmute.
So do we have some 12-minute presentation and question or just 15-minute presentation?
13 plus 2. We have been following that.
13 plus 2, okay.
Yeah.
Dr. Sundaresan, am I audible?
Yes, yes, now you are.
Okay. Good afternoon to everybody.
Hello, good afternoon.
Good afternoon.
Okay, thank you.
You can try to share your slide and see.
Okay, so for that I will have to share, na?
Yeah. Where you are to? It's now. Nothing limits happening here.
That is the one which is holding.
I'm not sure if am I audible? But क्या लगता है?
Then share at the bottom.
आवाज तो अभी सब ठीक हो गया लेकिन कुछ तो प्रॉब्लम ओ ये है इस शेयर करने के लिए इसको बंद
Share. Bottom only then share.
At the bottom, you can see share.
Bottom most start video.
Start video, unmute, and then you have that.
Third one.
Our control ಕೊಟ್ಟಿದ್ದೀರಾ?
So there are some share option is there. Yes.
Okay. खाली share हो गया कुछ नहीं.
Yeah, it's sharing. Wait.
Is it okay?
Yeah, wait, son. Still it's sharing. Your bandwidth is low, son. Here it is showing. Can you turn off? Shall I turn off your video? Just
Okay.
turn off your video.
Yeah. Turn
You
it
just
off.
make it full screen, sir.
Yeah, made it already.
Yes. It's take time. In your screen, you have some notification like that is there. Just minimize it with that one. In your right side. Cisco Apex notification. Box is there, sir. That just drag it side.
Yeah. Where is this?
Yes, in that right side.
This one.
Yes, this one.
Am I audible?
Yes.
Okay. So shared is it's showing. Then what do you see dragging? We have to drag.
First, you can drag it in. Leave.
Professor Sundaresan, am I audible?
Yes, good afternoon.
Otherwise,
Yusuf.
Good afternoon.
You share, sir.
Yeah, good
Is it
afternoon.
okay?
Sir, just stop the sharing.
Okay.
When you share, the share button is there. That time you just share the full screen, entire your laptop screen or desktop screen.
Okay. I have stopped it.
Wait, sir. Yeah, you just now press share button. Screen 1 or something it will show first.
Okay. Yeah.
First
Share
one.
button. No, there is mute, then start video and then share.
Share.
Yes. So now I have shared the document.
Yes, come out of sharing.
Can you try it, sir?
I've already shared.
It's not come. Can share again? It's coming. Wait, sir. I was asked for the control.
Yes, it's showing approve, decline.
You can do it, sir.
Approve.
I will take connection. Can make it full screen, sir?
It's already full screen, I think.
No, sir.
Full screen.
No, at the bottom, you can see that.
No, I think the typical screen button I have already pressed, and to me it looks full screen. Sharing, stop sharing, chat.
You just stop screen and again share it, sir.
Stop sharing. Stop
It's
sharing.
not coming for us.
So
Entire
you're not
screen you
able
can
to.
share. Entire screen you can share it, sir.
entire
Otherwise,
screen.
when you press share button, you can select the PPT. Otherwise, you have any disk, you can give the control, we'll make it itself. In chat section, I have sent a request for any disk. You can put it any disk number, I'll take it to control. Niranjan sir.
Dr. Lala? Hello? He's muted now.
Yeah. Now I'm.
Do you have any disk installed in your computer?
No, no disk.
Okay. So this, okay, I think now it's okay, but only the, can you change the slide?
Yeah, that's what I'm doing. No, it's not possible to change the slide.
Then I think you are not in the full screen mode.
Okay, let me. Okay, I am just starting everything first.
Hide. Not that one. Hide. Yusuf.
Yusuf?
Yeah.
You can share, try to share that slide now.
Okay. I was just trying and then closed it. Okay, I'll do it.
Okay, try, yeah.
This is a test one, so let me see.
You are in Mumbai or Bhubaneswar?
Sorry?
You are in Mumbai or in Bhubaneswar? I'm asking.
I am in Mumbai, sorry.
Mumbai, okay.
It's connecting very low transfer rate. It is normally connectivity is very good from here. Right?
Yusuf sir, can you turn off your video and try it, sir? Shall I switch it off your video? You can now. You can try.
I am doing it. Yeah.
Yeah, you can share now. You can try now.
Okay, I cancel and do it again.
Yes, sir. You just minimize this display. Oh, you log in with the browser. You just press hide button, sir. Hide, not that one. That hide. Not that one, sir. Hide. Sir.
Sorry, you are talking to me, right?
Yes, sir. Yes, sir. Yeah. You just minimize this display and make open your PPT.
The PPT is already open.
No. Just you put it in front, that PPT. Not here, sir. Just minimize this browser. Yes. Just click that one. Yes. Just make it full screen.
Yeah.
Yes. Slideshow. Start. Yes. We are getting full screen, sir.
Yeah.
Yes. Same like this only.
Yeah.
Thank you, sir.
Okay. So you can stop now. So you can follow the same procedure later.
Okay, so now let's see. Dr. Sundaresan.
Yes, please try now. Yeah.
I am trying to share once again.
Yeah.
So I have already pressed there. So the comment is this one. Share only the slide. So इसको पहले आप slide को open कीजिए. इसको open करें. इसको open कीजिए.
Niranjan sir, you just press share button, select that PPT.
Yes. ये तो ऑलरेडी खुला हुआ है वो. तो शेयर करेंगे तो only that one will come. अभी बस even if you change the screen. Okay, so are you able to see that?
अभी अच्छा आया सर.
Yes, we can see.
Okay. So
फुल स्क्रीन जाए तो वो इमेज आता.
Again, there are the two small windows are coming. Can you minimize that or drag?
WebEx Windows is there. Just minimize that one.
So I'm taking some help of some expert.
No problem. No problem.
Sure. Yeah.
So is it full now?
No, sir. Some Windows is open. You just minimize that. Otherwise, you can drag it somewhere.
On top of your PPT, there are two small windows are there. You know, some message is there. Can you just minimize it or drag down?
Okay. Now?
Take time.
No, sir.
No, still it is there.
So दो windows है. Sorry. Now?
There's a minimizing button is there now.
Hello? Let me drag करना.
I think one has gone down, I think. And the middle, on top of the middle one is still remaining.
Hello? Sir, are you able to see the screen?
Yes, we can see, but it's not in full screen mode. And then the small window is still open. It has gone. Okay, it's good now.
Make it full screen.
It's good now?
Make it
Okay.
just full screen.
I made it full screen, sir.
Gone. You just go PPT and remove presenter view.
Email. Okay.
Open the PPT then.
Yeah. I think that will be good.
You just escape it now.
Okay.
If you get in full screen, you escape it.
Yeah.
We are getting full screen.
Yes.
Yeah.
If you enable the presenter view, just remove it, that one.
And then?
In PPT.
We'll talk, yeah.
In PPT, one second.
They can mute now.
Stop sharing. Okay.
You can go next slide, sir. We will try it.
1 second. Share screen. Okay. View. Okay. Are you getting full screen now?
No, sir.
No.
Now we can open the PPT. Yes. We are getting. Go next slide. You can.
Okay.
Just press next slide.
Yeah.
Next slide.
So you're able to see now?
No, sir.
Okay. But to me it looks fine here.
Otherwise, you can. That PPT, it is possible to send, sir.
Okay. So I'll ask him to send you the PPT.
You can send it. We will share it here. You can go through like that only.
I think that is the best way. So which email?
Yeah.
Sir, which email ID you can send it, sir?
1 second. I'll hand it over to you. So they are telling me to send the PPT to you. I will send you the PPT and give me some email.
You can send it to me.
Sundaresh, you can send to Sundaresh, sir.
Okay, fine.
Sundar@jnc@gmail.com.
Okay.
Yeah. Okay. So.
Okay, thank you.
My slide.
ये कहाँ से होगा ये? Translate करना होगा. You can email. No.
All the other speakers are there. Okay. Anyway, I'm going to start now. No, I'll be 2 times I have to speak. Okay. So I just want to check the speakers. All the speakers are there now. Is Professor Nirmala there?
Yeah, I'm there.
Good.
Hello. Yeah.
And what I think I saw Dr. Ravi Prakash Singh.
Yes, sir. I am here.
Good. So maybe we can check during the coffee break because we don't have much time now. So we have a break at that time. You can check your sharing your slides. Then what about Aritra Banerjee and Dr. Aritra and Subha Majumdar? Okay, we hope that will join after some time. So good afternoon and good morning to colleagues in the UK and elsewhere, maybe good evening in Japan. So I have a few minutes to welcome you and then something to say about this program, the project. So as we know that the project assured access to all the beamlines of ISIS. So this was sanctioned in 2016 for 5 years, okay, about 150 days, 50 days of beam time, distributed in all the beam lines. And this was the sanction in 2016, and we started in 2017. And the PI of the project, as you know, is Professor Milan Sanyal. and I coordinate locally from JNC, and we have the project coordinator in Jayachandra here. And okay, so I just want to tell you that how we have done for the first several years, starting from 2017 to 20. So we have almost done 150 days of beam time. So as you can see here, and pointer, I will select this highlighter. Okay, so we received 211 application in the first call, and we could allot 46 days out of that. And then in the second call, 176 proposals received. No, sorry, it is not proposal, it is number of days requested, and then the days allocated. So 31 days we allocated. And then the third call, we received 288 days. And then we allocated 41 days. And then the last one was 181 days requested, and then 31 days. That 1 day was missing, and that has been, I think it is adjusted now. It's total 150 days. And except some days which are pending out of the last call, and maybe some of the calls in 2019 also pending, and that has to be completed. And so right now, as we know that things are not going well because of the pandemic, and still people are sending the samples and getting done, but as such, ICs postponed the present experiments. I hope that it will be taken soon because of the vaccine is coming up, and then they will also open up in the UK. So we'll be able to complete all the experiments soon. And we have also got, for this purpose, we have got no cost extension for next 1 year. That means March 2021. And this gives you an overview of number of experiments distributed on various instruments like WISH, MARI, MEOSAR, GEM, and EMU, and so on. These are all the number of experiments, number of days, which is shown here. And also we had also direct, we could support, in addition to Indian calls, we also supported several 14 days of 14 experiments of direct access. That means we apply directly to ICs and then they get beam time. So from the Nano Mission, we have supported so many experiments. And these are the distribution of people used in various places in India. And so these are different institutes involved in this. And of course, it requires a lot of expertise to data analysis that limits, and we are having a lot of, at least few, we conducted few workshops to analyze data. And the outcome of this project so far is, I received one more, so it includes 19 publications so far. Of course, it takes time, so it will take at least 1 to 2 years after the experiment. So we started in 2017, so this is not bad. And once we complete 150 days, I think we will be touching 40 to 50 publications from this phase. Okay. So, and we appointed first one postdoctoral fellow, Dr. Shivani Sharma. She spent time from March 18 to November 2019. She tried to, help the people from India, and also in data analysis and also collecting data. And now we have appointed Dr. Rajesh Tripathi as postdoctoral fellow, but unfortunately he could not go because of this lockdown in UK. I hope everything will go. And we conducted science meeting along with the steering committee meeting. So first meeting was on a one-day science meeting at Inorganic Chemistry Department, Oxford University, and where Professor Rao gave the prestigious RJB Williams lecture. And second time we had in JNC, that we called India RAL Neutron and Muon workshop, where we had a science meeting as well as workshop. And these are the speakers who came from UK and then also participated from India, speakers from various places, and then participants, about 50 students. And yes, this is about the workshop we conducted in February 7 and 8, 2019. And so this, as I mentioned, that we have got 1 year no cost extension to complete the experiments, and we may have to prepare the next phase. We need to work for that. I think a lot of people are interested, and this is a very good facility, and I think a lot of people benefit from this. So I think it's better to go for the next phase, but it requires a lot of work to be done now. And we suggest that whatever experiment we have done on the neutron, we should bring out a special issue based on, for example, diffraction and then magnetic structure, muons, and inelastic part. Like that, we should give the basics as well as the results. So it would be nice, we can create a special issue. And along with the synchrotron, I think we can bring together neutron and synchrotron, so that the Nano Mission will have a good, they'll be happy to support or extend this project further. And I think I complete here because the time is up. Now we need to start the next technical program. The first speaker in the technical program is Professor Sean Longreach from RAL, and he is going to talk on an overview of engagement of Indian researchers with the ICs, neutron and muon sources, a success story for international research collaboration. Professor Sean Longreach, please. You have 30 minutes and plus 2 minutes for questions.
Thank you, Professor Sundararajan. So what I would like to do, at the time available to me today, is to really, I guess, just talk about our collaboration, actually from the UK side, and it's something that we think has
once
been.
again, can you change the display settings, sir? We are
Oh,
getting
is it? Sorry. Let me maybe
in front. Yes, you just remove. Go to slideshow. Yeah, we are getting full screen.
Yes, it's fine. Yeah.
Is that good? I just wanted to find the pointer. There we go. Okay, thank you. Sorry about that. So yes, I would like to just to give you a view from the UK for the collaboration that we've enjoyed now. Actually, for many years, the ICES facility started to produce its first beams around 1985, 1986. And actually, India was the first international partner of the ICES facility, going all the way back to 1983. So this is a long-standing engagement. But I think what we've seen is that with the Nano Mission project, we've seen a step change in our interactions, and I'd just like to talk a little bit about those, if I may. For those of you who've not visited the Rutherford Afton Laboratory, I'd like to give you just a very brief overview of the lab, some of our capabilities, and hopefully stimulate, if you've not used us, to stimulate some interest in potential future collaborations. And then I'll summarize some of the metrics that have come out of the research program, which I think are very impressive, and as Professor Sundararajan says, are growing dramatically. As part of the Nano Mission project, as well as providing training, access, secondments, there's also been contributions to the Zoom small angle instrument, which is shown here in the background behind Professor Sharma. I'll tell you a little bit about that. And then very briefly summarize where we are and what we would like to do next. So this is the Rutherford Afton Laboratory, and the particularly interested in is the ICES neutron and muon source. This is Target Station 1, opened in 1986. Target Station 2 opened in 2009. And essentially this is the second target station is optimized for largely cold neutrons, so it fits in very well with the Nano Mission project. So for nanoscale objects or very large scale objects, complex magnetic structures and so on, it's an ideal facility. But of course, on the wider campus, we have Diamond, our third generation X-ray facility. We have big lasers, we have computational power, and so on. And so I think, as Professor Sundararajan was hinting there, this synergy between X-rays and neutrons is a very real thing from a scientific perspective, but also you can see geographically, it's a very real thing on the Harwell campus. So just to give you a feel for the scale of the lab and what we do. So typically, this is from our annual report for 2020, which has got a little bit of COVID impact, of course. We have a very large number of users, between 3,500, 4,000 user visits every year. And the number that I'm particularly pleased is that over a third of those users are new users. So if you're not an experienced facility user, that's not a barrier to you joining us and trying to do some science, because we have this very large flow through of new users, which we're very excited about. Overall, we have a large number of proposals, 1,600 last year from 40 countries. And of course, this very large student program. So over 750 students visited us last year. And this then turns into, all of these visits turn into 550, 600 publications a year. So a really, a very productive facility, and which compares incredibly well internationally markers against other facilities. So before I kind of just dive into some of the details of the Nano Mission program in particular, just to say, and I think this is a really important point, as part of the Nano Mission project, access has been secured to all of the instruments. So this is, we have roughly 30 neutron instruments, about 5 muon beams. Rather than just choose all of our activity on a certain number of instruments, it provides access to the whole facility. And I think you saw that in Professor Sundararajan's slide, which showed the instruments that we've used across the facility. Not only do we have the neutron instruments, we also have a lot of support laboratories, deuteration, which has been used by Nano Mission, the biology lab, materials characterization, where we have squids, X-ray diffractometers, and so on. So what are the kind of things that we've been doing? Essentially, I think it splits into 3 areas. The first, and by far the biggest, is our work with DST Nano Mission and JNC, which, as I say, has secured access to 150 days of beam time. Importantly, it's supported travel and subsistence for Indian visitors. You've heard about the scientific meetings, the training workshops we've had, the contributions to the Zoom instrument, and the secondments of Dr. Sharma and hopefully eventually Dr. Tripathi to us at the lab. There's also been an initiative in the UK in Newton Barber, which is an intergovernmental agreement to promote work, sustainable development, new materials, and so on. It's covered the travel and subsistence for Indian visitors. And also recognizing the success of the program, ARTIS as a facility has also supported travel and subsistence for, at the moment, 19 experiments. And we've also supported Indian students to attend Advanced Muon School and the Oxford Neutron School. And this is the picture you see from the Neutron School in 2019. And of course, we very much hope that we can get back to these sort of meetings in the not too distant future. So I can probably skip this very quickly. I think what it shows is that over years, the Indian engagement was at a relatively low level. And then, of course, what you see is the change as a result of the Nano Mission project. You can see that it was starting to build up, and then really this incredibly impressive growth. Of course, with that growth comes competition. And so clearly, because of we only want to choose the best quality science within the Nano Mission project, it's good to have an oversubscription. In reality, what these numbers tell you is, I think, about a quarter of the proposals were funded. So that's tough, I accept that. But to secure access to the facilities, I think you want to be sure you're getting the best science. So so it's well worth applying for time. I said I'd say a little bit about Newton Barber. It was a much smaller scale program, which ran between 2015 and 2018. And you can see we funded about 40 experiments. But really, I think what that helped was just to add to the momentum of the Indian community using our facility, which has generated such an impressive output. So I particularly like this slide, and it's a different take on Professor Sundararajan's. But in 2016, when we just looked at our user base, it was maybe a small number of labs, which I've shown here on the left. And on the right is 2020, when we look at the user base from all of those schemes, through Nano Mission, through Newton Barber, through the funding that the ICES facility has provided. And you can see there's just this really good distribution of labs across India, which is bringing us the high quality science. And you can see this is the number of unique institutions. I think we're up at something like 33 in 2020. So just a really big and encouraging increase in engagement with the Indian community. So what kind of science have we been doing? So in the bottom panel, I went onto one of our databases, so-called Web of Science, and it kind of balances out the different things that we do. And you can see, so we do a lot of condensed matter research, a lot of material science, applied physics, a lot of chemistry, nanoscience, and there's some, sorry, it's hidden on my screen here. There's a small amount, but nonetheless significant, of biochemistry in drug delivery vehicles. So we've covered a large range of areas in the program so far. I think energy and environment have been quite strong. Next generation materials, battery technologies, solar, sequestration of gases, some engineering aspects at the nanoscale. As I say, a very strong and I would argue world-class program in quantum matter. And also a small number of proposals in healthcare, with some nice examples in next generation drug delivery vehicles and so on. And here what I've just tried to do, and it's a very sort of coarse analysis, so I apologize, and I realize I've kind of hidden the y-axis here, but this is just the number of citations that the work with India has generated. And so you can see there's this kind of nice build up in sort of 2010 onwards, but you see this step change. So this is 2016, this is the Nano Mission agreement. 2017 is when we actually issued our first call. And of course, we know there's a lag in time before publications come along, but there's just a really nice rise in citations, which I think shows that we're doing high quality, high impact work within the Nano Mission project. I should have deleted this point. Clearly, we've not got data here, so please ignore that, and apologies for the poor presentation of the figure, but you can see really nice build up. I said just briefly we would talk about the Zoom instrument. So Zoom is a small angle instrument which has been partially funded through the Nano Mission project. It's quite an ambitious experiment, an instrument, sorry, which is really nicely optimized for magnetic thin films and grazing incidence, small angle scattering. Turns out the first paper wasn't on a magnetic system, it was on a polymeric system, which I show here. First experiment appeared in Nature, so clearly a high impact work, probably because they were able to produce self-assembled polymer rings that look like the Olympic rings. That's probably what got everyone's attention. But actually, we've been doing a wide range of experiments, and here's some work from Professor Surinder Singh and Basu, in this case at VARC, looking at domain structures in a complex oxide system. So there's lots of exciting science going on the Zoom program. So I'm aware that there's many great science talks to follow, and I don't want to delay those. But hopefully I've been able to convince you that there's been a real step change in India ICES interactions, which has delivered a very broad range of nanoscience and training. And as Professor Sundararajan says, we have some work to do now to secure the new agreement. There's a lot of enthusiasm on both sides of this collaboration to do that. And we're already thinking about the levels of access we would want and possibilities in advanced sample environment. And I'd like to finish really by really truly thanking colleagues in India and ICES from the vision of Professor Siana Rao to make this through to the works of Professor Sanyal Sundararajan from JNC, Professor Nagaraja, Professor Kulkarni, Professor Sood on our governing body, which has sort of steered the direction of this project. And at ICES, I'd like to thank Professor Roger, I think is our next speaker, and Evie. And thank you for listening to this talk and perhaps not listening to the cricket, which I know at the moment is at a very delicate phase, but has given us lots of enjoyment in these difficult times. So I'll stop there and thank you for your attention.
Thank you, Dr. Sir. Is there any questions? Thanks, that you can read. You switch on your.
Hello. Yeah, one question is there. Can you comment on the application of muon force in the study of magnetic monopoles and magneticity?
I'm sorry, I didn't catch that. Yeah, I heard muons and
Speak clear.
Yeah. Can you comment on the application of muon source in the study of magnetic monopoles and magnetricity?
So the muon is different to the neutron probe in that it's not scattered, it's implanted. And so when the muon implants in a system, for 2.2 microseconds, it processes and it senses its local field. So it senses any kind of processes that occur in the vicinity of that muon, whether it be diffusion in the case of ion diffusion, say in batteries. So you can study, let's say, lithium or sodium diffusion in a battery. And similarly, if you've got objects, so you talk about monopoles and a flow of current, then the muons will be sensitive to that. So there are quite a number of publications now on these systems, and you're really taking advantage of the sensitivity of the muon to its local environment, whether that be an unconventional superconductor or whether it be a skyrmion hosting material. You're able to extract interesting information. And there's a quite challenging experiments still, but they can be done, and there are examples of that from the Rutherford facility.
Is there any questions here? Okay, if not, thank you, Professor Son, for the nice talk, introduction about the overall usage, and then about the Indian Nano Mission access and so on. So thank you very much for sparing your time. So the next talks will be given by Dr. Adroja. So he will be talking on orbital effects and spin dimerization in barium-4 Ru3O10, neutron scattering and muon spin rotation studies. Dr. Adroja.
Morning, good afternoon, and good evening, everyone. And I would like to thank the organizing committee for providing the opportunity to present our work. And this is a very nice, interesting workshop. I attended many talks since morning 4 o'clock. It looks very interesting program. So what I want to talk about this compound barium-3 ruthenium-3 oxygen 10, just to see the spin dimerization and orbital effect. So we carried out the neutron scattering and muon spin rotation study in this compound. The project was started in collaboration with Professor Majmudar from the Calcutta, and also Juma did a lot of work. She was the postdoc at ICIS, and Anup Bera did analysis of the spin wave. And also a group from the ICIS Renewal and MEOSR and neutron experiment. And Professor Das Gupta did the theoretical work. So if I have time at the end, I'll also show something on the honeycomb lattice, which we did work with this Amitabh Bhattacharya and Professor Sinha, and then give some short summary. So the question is this spin chain system, like spin chain system, you have the half integer and integer spin, and what are the interesting things? So if you have the half integer spin, the excitation spectrum of the triplet is the gapless. If you put tiny perturbation like anisotropy or interchange coupling or alternative exchange, then you can open the gap, and also you can open the long range excitation, long range magnitude order in this one. But if you have this integer spin chain like 1, 2, 3, then there's a robust gap in the spin excitation, and this is called the Halden gap. And Halden gap has taken a lot of interest in the recent condensation physics. So the value of the gap is directly related to exchange parameter. So if you have the spin 1, then your gap is 0.41 times J. If you have spin 2, then your gap is reduced. So this is a very interesting thing to study by the neutron, because neutron can directly probe the gap. And here the reference is on this Halden gap. So the question is, why the ruthenium compound? What are the interesting in the ruthenium compound? The ruthenium provides a nice opportunity to go to quantum to classical medicine, because ruthenium has various spin 2, ruthenium 2 plus has a spin 0, 3 plus has spin half, 4 plus spin 1. So you can have Halden gap in that one, and ruthenium 5 plus spin 3 half, you can get a classical limit. So this is a very nice system, the ruthenium. There's so many interesting work has been carried out on the ruthenium compound. And this is one of the compound is ruthenium is pyrochloride lattice. It's cubic system at high temperature. If you cool down below 150 Kelvin, you show this orthorhombic transition, and then also open the metal insulator transition, and then open the spin gap, sharp drop in the susceptibility. So what this Daniel Chomsky did this calculation on this compound. He found there are the orbitals are playing important role. So if you have the XY orbital, there's no overlap. So if you go to this red one, there is no overlap between these orbitals here, and these are the inactive like orbitals which are not playing much role. But if you go to this YZ and ZX orbital, there is overlap here. So basically, it provides a 3D network in this a 1D network in 3D material, and that provides the possibility of Haldane gaps. And so they estimate the J's, and the J's basically gives you the spin gap of 9.4, while experimental observed gap is 11 MeV. So there is a possibility, even if you have 3D structure, you can have the 1D interaction because of the orbital, and you can have the Haldane, possibly Haldane gaps. So this is the compound which I am going to present, the barium from ruthenium 3O10. And this is also a big compound. There are 2 barium side, 2 ruthenium nuclear side, and 4 oxygen nuclear side. So if you look at the structure here, there's a trimerization. There are 3 ruthenium. In the center one is the ruthenium 1, and other 2 are equivalent ruthenium 2 side. So there's a trimer unit. So the question is that what is the magnetism or what is the excitation of this trimer unit coming in this material? So that was the main idea, to understand this magnetic property of this material through the neutron and muon. So here is this susceptibility. If you see high temperature susceptibility, the maxima here, and that tells you something like the dimerization or short range magnetic correlation. But if you go below the 120 Kelvin, the sharp drop, and then the derivative show the peak, which also agree with the heat capacity, which tells that at below 107 Kelvin, the long range magnetic ordering, which is the seen in this muon. So here's the muon. So muon is, as Sean mentioned, that muon is a nice probe. And if you put the muon in the material, it sends the local field, it precesses, and the precession frequency directly measures the what is the field at the muon site. And if you saw this, if you go to the here 110 Kelvin, which is the short range order, muon doesn't seem much because the time scale of the muon spectroscopy is different than the fluctuation time, so it doesn't seem much thing. But if you go to this order state, you can see nice frequency here, and if you go down, frequency is increasing, and then basically it tells you that there is a internal field in the material which is for the long range order. So you follow this frequency as a function of temperature, you can just get the order parameter, and by fitting those temperature different frequency, you can estimate the exponent. And if you look at the exponent 0.37 critical exponents, now if you compare with the theory, basically the 3D Heisenberg system has the same value of the exponent. So it clearly tells you that this is the 3D, even this system looks like low dimensional, so system is the 3D materials. So now let me just show you these are the where if you have the material, you can look at the asymmetry in the muon, and if you have full drop in the asymmetry and there's just one component, so basically what it's telling, there's only one ruthenium side orders magnetically, other side is paramagnetic, doesn't order it. And you can see these frequency components come up, so volume associated with frequency is coming up, and volume associated with this longitudinal component comes down. So this is telling the bulk long range ordering, and you can see the peak in the lambda, which tells the fluctuation near the tissue. So then we did the neutron diffraction measurement on the WISH diffractometer, which is the powerful diffractometer, because you can study the long range magnetic order, which is larger d specific because of solid methane moderator, huge flux. And what you can see the data here, that 155 Kelvin, you can fit the nuclear structure. Once you go to the 1.5 Kelvin, you need to put this extra magnetic peak. And magnetic peaks are very small. It's very small, only one clear peak, see the remaining coming on top of this nuclear peak. But what you can see that this magnetic peak gives you propagation vector 1 0 0 0. So it is k equal to 0 magnetic structure, antiferromagnetic structure. And as we've seen this from the muon, only side orders, this side doesn't play much role. So if even you look at the irreducible representatives, there are 4 irreducible representatives, but this side is not playing much role in magnetic ordering. So only the ruthenium 2 side, which is the outer side of the trimer, is playing a role. And there are 8 irreducible representation. This 7 one is ferromagnetic, but system is anti-ferromagnetic, so we can ignore this one, and then you can fit with the gamma 6, which is the basically moment along the a-axis. Gamma 8 is moment along the b-axis, and you can clearly see the moment along the a-axis fitting nicely to this data. So this is the basically gives information on magnetic structure, and here again you can look at the order parameter through the neutron diffraction, just plotting the intensity as a function of temperature, and you can see here. So this is the magnetic structure Zuma has obtained from this neutron diffraction on the WISH data. And what you can see here, this ruthenium 1 is non-magnetic, and there only the ruthenium 2 side orders it. So you have the trimer unit here, and you can see antiferromagnetic coupling. And if you look at the second trimer, there are a couple antiferromagnetic. Also, you can use the ferromagnetic plane, couple antiferromagnetic along this axis. And this is the moment comes 0.89 Bohr magneton, which is the smaller than you expect from this spin one moment. And also this is agreement with this other report which passed the DD. They said the moment is along the B axis, but the real moment is along the C axis. But they found only one peak. Like we had this many peak in this data. So now if you look at the octahedra, the ruthenium-1 and ruthenium-2 side, they behave differently in the temperature. Like this two oxygen comes in and this other expanded. So if you look at the function of temperature in the ruthenium-1, this ruthenium-1 oxygen-2, this bond is basically is not much temperature dependent, but this bond shows this strong temperature dependent. And you can take this difference of this ruthenium-1 and ruthenium-2, you can see continuously change in the bond length of these two, average bond length of these two octahedra as a function of temperature. Also, their lattice parameter decreasing at Tn, which again coming from this magnetoelastic coupling. And you can also use this bond valence sum, and you can estimate the average change in valence from 2 minus 1. And this is again saying the valence is increasing a little bit function of temperature. Basically, you require spectroscopic evidence for to see real valence, but this is just gives idea of this one. So now these are the DFT calculation. Then DFT calculation tells that there's a crystal field on the two different T2, this is T2G level splitting, the two different sides of ruthenium-1 and ruthenium-2, while ruthenium-2 side is a very small crystal field splitting, so basically that stabilizes the spin equal to one state, but the ruthenium-1 side is huge crystal field splitting, and that basically stabilizes the spin equal to 0 state, so that gives the non-magnetic state, but the EG levels are very far away from that, and the crystal field splitting of T2 to EG is 3.7, and the Hund's coupling is very small, so basically it gains the energy by stabilizing the S equal to 0 state in this compound. So then we did the neutron scattering on the Merlin with Merlin time of flight spectrometer, where you can estimate this excitation as a function of the Q, but this is powder, so you can see the average Q. If you're single crystal, you can see a lot of information, but this is powder, you can see the average Q. So you can see mode Q versus energy, and you can see the excitation starting very weak from 15 MeV and around this 30 MeV strong excitation. And you can look at the cut in the Q, or you can make the cut in energy, and these are the cut I plotted from this data at 5 Kelvin. What is telling that there is a gap around 15 MeV in this data. So if you look at the low energy data, so you can see the high temperature, you have some excitation around 7 to 8 MeV. And we're going down in temperature, this excitation disappears. So what is telling that once you are in short range order state, you have some sort of dimerization gap. But this again, if you look at the Q dependent of this gap, it's saying these modes are not 7 or 8 MeV modes are not purely magnetic. They also fall on there. So it's just basically magnetoelastic mode, you can call it. And now you can analyze this data by using the spin W, because system is magnetic order. So you have the J1 between the timer, this outer timer, and then you have this J2 and J3 here. And if you analyze it, it's like Juma and Anup did the analysis, and they find this 20 MeV strongest within this timer unit, and the 9 and 1 MeV J3. So if you look at this ratio of the J1, J2 is 0.4. Now the question whether this is the Helden gap or this is just dimerization in the system. So if you look at this phase diagram, the delta versus this ratio, and you can see if you are in critical value, you have this in the one side is the Helden gap, other side dimerization. Now our data basically comes in this one, so it's telling this is the basically spin dimerization in the magnetic order state once you are in low temperature phase. So then we also calculate this DFT J's, and these are the value of the J's from the DFT, GGA and GGA plus U, and then you can see these are estimated from the neutron data, which are very well agreement with this, and that's also agree with the past measurement with people did it calculation. Now let me just spend 2 minutes on this honeycomb lattice. This is distorted honeycomb lattice compound, and you can see if you look at this system, is honeycomb, but it distorts it. Basically, you can assume as a change. So you have this the lithium and copper distorter. So it basically gives you the copper here, and then in between it comes as lithium, green as the lithium. So it breaks the chain. So basically you have this limited number length of the chain in this compound, and the susceptibility gives you the exchange parameter reported here there. But this is the spin half, couple spin half. So you can also couple the two spin very strongly. You can put spin 1 and a couple anti-family, though you can also have the possibility Helden gap in spin half chain. But we'll see what this is real handle because Japanese J's are very strong here and then weak between these two. So it tells you this is held type phase, but let's see what we see it here. So this is the MUSR measurement we did it, and zero field MUSR doesn't show any long range ordering, but it basically shows the two component. And this beta basically tells you that if you have the beta 1/3, you can spin glass. But here there's no beta is going up. That means this is short range ordering, but not in the spin glass. It's dynamic fluctuation in the material. And this is the neutron scattering data, which experiment was carried out on the Merlin. And you can see this is the data. This is the higher energy, then decreasing energy. So you can see the three excitation. One is around 30 MeV, then double excitation there, and this one. Even though this is, yeah, just finish.
Yeah, thank you.
The system is not magnetic order. Yeah, I'll finish it. Yeah. So it shows the spin wave, and then this is the exact diagonal calculation, which basically shows again the excitation, but basically even there's no longer the spin wave models exist very well. And this data clearly tells that the anti-ferrometric J's are much stronger, even distance is very big here because it's super exchange, this an orbital effect, this exchange are much stronger than this even smaller distant exchange. And that basically tells this system is the anti-ferrometric alternative chain rather than this Helden chain. And here's my conclusion basically what is showing that we have this magnetic ordering the barium. Yeah, and then I think thanks very much for the Professor C.N. Rao starting this Nano Mission program. Also thanks to Professor Sundarsan and Milan Sanyal and managing the program very well. And thank you very much.
Raja, you can have one short question.
Yeah.
Yes, you are Rajesh.
I have a general question.
Yeah.
Hello, sir. Can you hear me? Hello.
Yeah.
Yes.
So can we base our?
So I can't hear the question.
Do you see?
Hello.
Yeah.
Hi, sir. So I have a general question. So can we calculate or even guess the magnetic moments of the ordered moment by by MUSR experiment as like neutron?
Yes. What you can do it, you have now magnetic structure, you simulate the dipolar field, and you vary the moment of the deuterium when your frequency agrees with this MUSR of the frequency, that is the value of your moment. So you can do that thing.
Okay. Thank you. So thank you. And so we don't have time, so we could have taken more questions. So thank you, Dr. Ahuja.
Yeah.
So let's move on to the next talk. This will be given by Professor S.M. Yusuf from BRC. He is going to talk on recent magnetic neutron scattering studies on Na2CO2 TeO6 and NdFeO3. Professor Yusuf.
Yes. I'm trying to share my. It's connecting. I'm sharing the file. Bit slow. Do you see the graph?
No, we don't see. We don't see.
Sorry?
We don't see your slide.
Okay, I can start, right?
No, we don't see your slides.
You don't see?
Yes, we don't see.
No. Can I start?
Can you share again?
No, I am sharing only. It is.
No, we cannot getting then. You just stop the PPT and again share it, sir. You just go back.
Yes.
You just close the PPT. Yeah, now you can press the share button. Select that PPT.
1 minute. I have already pressed the share button. It is showing connecting. It is
Just stop
doing
the
round
share,
and
sir. We cannot get any share screen.
okay.
You can try it now, sir.
Share
No, sir.
file.
No, sir. We are not getting. Anything? Hello, sir.
Yeah.
Yeah. Now it's coming. Coming. Wait.
Okay.
You just minimize this one. Yeah, hide button, you can press it. Yes.
No,
Just,
I see your file.
No, we can see your file.
No,
You can
this
make
is the wrong file. I didn't want to. Yeah, this is the one.
yeah, you click it, double click it. It's still loading.
I think too many files are open.
Okay.
Is it okay now?
Yes. You just make it full screen. Slideshow mode. Yes, sir.
I think it is okay now.
Yes, sir.
Please go ahead.
Go.
Yeah.
Yes, is it okay?
Yes, please go ahead.
Yeah. So thank you so much for all the support which you have been getting from this project. And so today, what I'll do, I'll give a very brief overview of what we have done so far on these three different systems. And the first one is on the possible KEK model using this 3D cobalt. And here my colleague Dr. Anup Bera is involved. And the second one, then I'll move to this rare earth magnetism with regard to NdFeO3. And this is a continuation of our earlier one, MnO3, which we published in Physical Review. Here, Dr. Amit Kumar mainly involved, and also Dr. Anup Bera for data analysis. And the third one is where we will be talking about this cathode material, possible lithium-ion battery-based material. So I'll just touch upon all these three. So first one is the title of this talk is Realization of KEK model in the 3D ion-based honeycomb antiferromagnet Na2CO2 TeO6. So here we are dealing with the cobalt magnetism, and the question is, can we have the KEK state out of this 3D electronic state? And here is the as per the theoretical approach, the spin half level honeycomb lattice, if we take, then this is the Hamiltonian for that. And here you see only the KEK term, and this is the Kx, Ky, Kz, and you see the exchange, the bond dependent, whether it is between X, Y, and Z direction. So this is and it is exactly solvable, and theoretically it has been shown this kind of superposition of entangled states, quantum superposition state, and can we have the experimental realization? That is the problem we are dealing with. And here you see how this bond dependent exchange along X, Y, and Z is possible, is foreseen theoretically for this kind of honeycomb lattice, and we will try to have experimental realization. And this has a very good implication in terms of the quantum spin liquid behavior, as you see, and I will not go into details. Now the question is, in the literature, of course, it is known that the 4D and 5D elements, particularly consisting of iridium and ruthenium, they have shown, particularly these literature reports are there, they are good candidates for this kind of Keter model. And what you see here, and what is basically shown here is the 5D state, 5D5. If it is under crystalline electric field, what you see the splitting of the state to EG and T2G, and this is what is the electronic configuration for the 5 electrons. But now the same thing, if you put under, now after this state, if you put under the spin orbit coupling, then there is a further splitting, and eventually one gets the J equal to effective half state due to spin orbit coupling. And this state shows this pure Keter type of phase. But the question is, can we have, question what we have addressed, can we have this kind of Keter model, Keter phase, the quantum mechanical phase, this in a 3D based system. Here is particularly the cobalt 2+. Now there is a theoretical work on this cobalt 2+ based system in this paper, where it has been shown that let's say cobalt 2+, 3D7 state, if it is under crystalline electric field, this kind of splitting. But on the right side, what I'm showing, if it is under spin orbit coupling, then the system, even the 3D element, that is cobalt 2+, can effectively show that J effective is a half state. So that means if that is so, if the theoretical prediction is right, then even in this kind of 3D based material using cobalt 2+ can have this Keter phase. And this is what we have addressed experimentally. Experimentally, our system is Na2, CO2, TeO6. And this is we have done all the detailed measurements, and we have this is the crystal structure, and we are interested about COO6, and cobalt forms this honeycomb lattice. As you see, these are the cobalts, honeycomb lattice it forms. And here, if you see, and at the center it is tellurium, and if you sit on one cobalt, and the surrounding is, if you look at the exchange, then you can have this kind of either from this cobalt and another one neighboring, let us say this one, you have J1, then second nearest number J2, and third nearest number J3. So this kind of bond dependent exchange, see this kind of J1, J2, J3 it could be possible here. Now we'll go further and see that we have done the neutron diffraction, and prior to that, the susceptibility measurement. We do see the magnetic phase tension, the antiferromagnetic tension, 24.8 Kelvin, and we have also solved the magnetic structure, and this is what is the magnetic structure, and this based on the cobalt, the honeycomb lattice, and this kind of magnetic structure, planar structure. So this is very important because the 2D structure, 2D magnetic ordering is established in this case, which is very much ingredient. Low dimensionality is ingredient for this kind of Keter spin liquid kind of state to exist. Now, what we have done at ISIS is in collaboration with Dr. D.T. Adroja, is there online, and here what is expected here, that if you have J effective half, and then that is after, see what I show here, these three states after the spin orbit coupling. Now let us say J effective half and J effective 3/2 and 5/2, they are again subject to trigonal compression, because this cobalt is sitting in the trigonal site in the crystal structure we have seen. Now there will be further splitting and shift of the energy levels, and then if we again switch on the magnetic perturbation with magnetic ordering, then there will be further splitting. So that means if we see this system, where this one Na2CO2 EO6 at low temperature below the Tn, that is 24.7 Kelvin, below that, if you do the experiment, which you have done at 4 Kelvin, let us say, in this case, what we would be expecting, that these three tension lines. Now what, and if you do at higher temperature above the magnetic ordering, where there is only crystalline electric field is there due to trigonal this distortion, so there we will be only seeing one line. Now this is what our experimental data at 40 Kelvin, which is above this Tn. So 40 Kelvin we expect this, and this is what is the 40 Kelvin data intensity as a function of energy. We have one line, so this is due to the crystal field effect. But if you do experiment, and that is what has been done at 4 Kelvin, we see that the other transitions, other lines, excitations, okay? And here, this one, so that the higher energy one is the crystal field, lower energy the spin wave. Now, what is show here that at 4 Kelvin we have 3 lines. This is the green one is this, and blue one is this, and the other one, the pink one is this. So we have 3 lines. So this establishes that effectively this this state is half. First one. Yeah. Now, so J equal to J effective half is established here. So this has that means the real ingredient to have the kitted model in this system. Now we go further. Now what is done here? This I show the low energy states. They are that around 3 millielectron volt. Now this is due to the spin wave, as I said, and this you see the dispersive one at lower energy. Now if we take only the J1, J2, J3 model Heisenberg type, then what you see, this is the theoretically calculated expected, which does not reproduce the experimental observation. But if you take the Kitev and the Heisenberg model combined, then it reproduces the experimental observation. And from that, we have considered this Hamiltonian at this exchange. This is the Heisenberg term, and these are the Kitev term. And we have measured this exchange strength. So that means this exercise, this measurements at ICs tell us that we have possibly got a system at this Heisenberg and Kitev model is applicable, and this is almost ready for submission. Now, but so far the results which I showed, those are on the measure on polycrystalline materials. But as you see, as I have been telling, that bond dependent exchange, if you have to establish, that's why we have grown single crystal, and it has been characterized. This has been made in our lab using 4-meter furnace, and in the magnetization along different directions, you do see anisotropy, because anisotropy is very highly is strong ingredient to have this Kitev phase. And then we have measured the diffraction with Dr. F. Alangdi, and you see that we do see that the field dependent anisotropic properties. So this part is done. But what is then remaining is that inelastic study on this single crystal sample. That is what we have to do in future at ICs, and I'm sure the agencies are keeping a note on that. Will be submitting a proposal. Now I talk about the next system, that is NDFeO3. Here physics is slightly different. Here we are dealing with the interesting rare earth magnetism, and though perovskites are well known, but rare earth magnetism in this kind of system is hardly addressed by using microscopic technique. And if we talk about this comets, the 3D is chromium, or 3D is iron, or 3D is manganese, the structure changes. So here, whether it is G type, both cases, but here A type and E type possible, depending upon the what kind of crystal structure, orthorhombic or hexagonal. From LA to DY, larger ionic radius gives orthorhombic, and then A type structure, this the higher rare earths with hexagonal crystal structure gives A type antiferromagnet. But what is the role of, so all this understanding with regard to only the transition metal, that is chromium, iron, and manganese. But what about the rare earth? Rare earth, this is not known. What is playing the rare earth? What role is playing? So we have done detailed measurements down to 1.9 Kelvin, and you see using this GEM instrument, and we have done the analysis. This is the magnetic structure. So the good part is that, of course, this transition metal iron, and this shows same magnetic structure what has been reported for the literature and expected. But what is the new piece of information about the ND ordering with this kind of this ferromagnetic component, net ferromagnetic component with this antiferromagnetic? So this is what is established here as far as the ND ordering is concerned. So this is new piece of information. Now we have also grown the single crystal of the same using our 4-meter furnace, and this is a large crystal as you can see. And then we have done inelastic study even using ICs. And here what we show here is the higher energy modes, excitations, and then this gap you see, and this gap has been theoretically we have reproduced by doing the calculation. But here at this for this energy, we have only considered the iron, the 3D, and all these parameters have been derived. And this is the Hamiltonian. This is the Heisenberg term. This is the Joule-Moria term, and this is the anisotropy term. But we have also done the analysis and experiment with regard to the low temperature data, looking at the low energy excitations. And the low energy excitations, for low energy excitations, not only the iron ordering and iron plays, exchange iron participation in this excitation, you see also role of ND there. And we have also estimated all these exchange strengths, iron and ND, and with their proper side. So this part, so coupling between Fe and ND has been established. Now the very last one. Sorry?
1 minute, because already time is over. If you want 1 minute, otherwise question and answers, we need to have something.
Okay, just I'll say that, just one statement I'll give. Lithium this material is very suitable for the cathode material, and it shows anisotropic properties. We have grown the crystal, single crystal, and then we have done both the diffraction experiment and the inelastic experiment. And we have shown seen the excitation. This is the crystal structure, nice structure. We have got without any twin, and also then we have done the magnetic structure, and then we have measured the excitations. This is the possible magnetic structure, and then in inelastic study we have seen the acoustic phonons, and we have also seen the optical phonons, and we are analyzing the data. Thank you so much.
Thank you, Yusuf. We can have one quick question. No?
Yeah.
No? Looks like there is no question. So okay. So thank you, Yusuf, once again.
Yeah. Thank you. Thank you.
Thank you. We will move on to next talk. It will be given by Niranjan Prasad Lala, and he is from UGC DAE, and he is going to talk on time of flight neutron scattering studies on substituted spinels, chromium spinels, and spin structure of spin-oriented phase in samarium chromate.
Am I audible, Professor?
Yes.
Okay. So let me start. So before I go to slides, I would like to thank the organizers of this meeting and for providing funds for all the experiments done by the students, and for giving chance to present few of the results which we got those experiments. So basically today I will be talking about the results of two experiments which were done RB 176029 and something similar which was done in some time in October 2018. And okay, let's go back, please. First slide only. Okay, and the latest experiment which we did on 2019, that was for another physics work of another student, and they are the collaborators with Evan Silva from the JNCASR and Pascal Manuel, and then Shivani Sharma, Rajamani, Tekla Petrusek. Okay, next slide. Yeah. So regarding the work on spinels, I think all of us know that AB204 type of spinels have octahedra and tetrahedra in their structures. The B type of and cations are surrounded by octahedral arrangement of oxygen, in which the octahedra share their edges, such that therefore the atoms, if it's the magnetic atom, then their T2G orbitals overlap, and it gives the chance that they can have a direct exchange interaction between them. And they basically the order of a tetrahedral topology So if they are having an interference interaction, then they can undergo frustration and result into very interesting ground states, magnetic ground states. The other cation, A-type cation, there is at the tetrahedral side, tetrahedral oxygen arrangement. So by controlling the John-Taylor effect at the A side, it's possible to control the interaction, change the structure, and thereby control the interaction between the B side. So the example which I am going to discuss is the nickel chromium ferrite, in which we have replaced nickel. Next slide. We have replaced nickel by two different type of cations, manganese 2+ and copper 2+. So this manganese 2+ is non-John-Taylor, so it's expected that it will not cause any deformation. That was expected, and the chromium copper 2+ is John-Taylor ion, so it is expected that it will change the structural deformation in the lattice. So you can see the pure nickel chromate has an elongated type of tetrahedra, and therefore we are getting a tetragonal structure, whereas by this 25% substitution of manganese +2 at the place of nickel has made the structure again cubic, and it changes the magnetic behavior. I will just show you. But by changing the copper at the place of nickel, you can see the deformation definition has changed. Now it has got extended along the axis. So basically the octahedra has got flattened, the tetrahedra has got flattened. So the expectation that they will change the interaction, they will change the John-Taylor effect has been seen through X-ray diffraction. Next slide. Okay, so these are some low temperature XRD measurements where you can see that they also show magnetic structural coupling. So across this first interferometric transition in the case of manganese, right down to 120, it remains FD3M cubic, and below that it becomes tetragonal. Of course, there is small region of coexistence. And in the case of copper substitution, the structure becomes tetragonal right at room temperature, and we cool it further, then something around 150 Kelvin, it undergoes tetragonal to orthorhombic phase transition. And below that also there is a minor change, which is seen in, you can see that there is minor change in the lattice parameter, that is going to be the next interferometric transition. Next slide. So it can be seen that in pure nickel chromite we get two interferometric transitions, TN1 and TN2. But when you substitute manganese, this second transition disappears. Actually, the system remains cubic up to roughly 70 Kelvin, and below that it becomes totally, it remains tetragonal. And whereas in the case of copper substitution, the transition temperature shifts to higher side, from 75, around 70 Kelvin to 95 Kelvin. And similarly, the second TN2 also shifts to higher side. So basically our interest was to study the frustration. So we fitted the Curie's law, and they found that this Curie's temperature basically changes and is largest in the case of copper dope, and of course it decreases in the case of manganese. And of course transition temperatures also shift. So frustration index basically found to decrease. It was expected to increase, but it is found to decrease in this case of here. In the next slide. Okay, so just to see that what really happens in the case of manganese, because although the frustration index is decreasing, but what we find that at lower temperature, in low temperature, take 10 Kelvin, there is a hump appearing at the higher angle, at the higher DST side. It tells that there is a certain manganese and chromium atoms, it still remains unordered. I will show you the table. In the case of copper substituted samples at 77 Kelvin, we found one ferrimagnetic structure which is given here, whereas in the case of 10 Kelvin, the same compound, just the antiferrometric structure changes because it shows two antiferrometric transitions. Next slide. So the refined moments, if you see in the case of manganese, the refined moments, the manganese moments, the moments at the A site, they are roughly 1.8 in the case of manganese dope, the sample, and it roughly remains of the nearly similar. Okay, sorry, the chromium moments, they remain 0.79, where they should have been roughly 3. So most of the chromium moments remains still frustrated even at 10 Kelvin, whereas the magnetic measurement doesn't indicate such thing. So that is the use of that is why the neutron scattering was done. That it shows that most of the chromium movements, they still remain frustrated. Where in the case of copper substitution, at 77 Kelvin, where the structure is orthorhombic, the moments and the magnetic structure is ferrimagnetic, linear ferrimagnetic. The moments are roughly 0.5 mu b, which basically changes to roughly almost to 3 mu b when it gets ordered. So what it says that even after distortion of the lattice to orthorhombic, there is still some chance of the, okay, so the frustration is not relaxed. It relaxes only when we cool it to 10 Kelvin. So this work was published in JALCOM. Next slide, I will just conclude in the last for both this work. Okay, so next work belongs to the structure determination of rare samarium chromate. Samarium chromate is basically an old compound that has been studied by many people, but due to the problem of neutron absorption, too heavy neutron absorption, nobody has directly studied the neutron structure directly. But what is expected that by other people by using indirect. Next slide. Okay, so what is expected? Okay, go to the first slide. Sorry. So in these all these chromates or these rare chromates, there are two magnetic ions. If the rare ions is also magnetic, then these chromium ions basically they form a ferrimagnetic arrangement. So there will be a ferrimagnetic component along the c-axis of the PBNM lattice, and this rare ions, although they are ordered at very low temperature, but they get polarized sort of, and they get antiferromagnetically polarized, and they try to minimize the magnetic field, internal field by the tensor metal systems. And in some samples, this becomes very large and results in a negative magnetization. And at a still lower temperature, so this ferrimagnetic ordering takes place at relatively high temperature, but at a still lower temperature, this antiferromagnetic interaction basically leads, supported by the magnetic anisotropy, leads to a total change in the spin orientation, and that is termed as a spin reorientation transition. Next slide. So these are some slides from other workers which show that the negative magnetization, for example, gadolinium chromate, samarium chromate, and lanthanum potassium chromate, they really takes place. So what we see here that this part is showing a negative magnetization, of course, in field cooled samples, and at still lower temperature, the magnetization drastically jumps, which corresponds to the spin reorientation. Similarly, in samarium chromate, the vertical jump corresponds to the spin reorientation. In chromates, mostly it is reported that the very first phase, the antiferromagnetic phase, the ferrimagnetic phase is a gamma 4 phase. Basically, it's most of the component is having a GX. Most of the moment components are having a GX type of magnetic ordering, whereas in the case of a lower phase, that is spin reoriented phase, it is a gamma 4 phase, where the spins most of the component of the chromium is lined along the c-axis. There is a GJ component. But of course, there are other opposite examples also, that, for example, neodymium chromate. Next slide. Neodymium chromate shows a totally different behavior. It orders in the gamma 2 phase at high temperature and then goes to gamma 1 phase. So these compounds show very interesting properties. For example, dysprosium ferrite, of course, it is ferrite, not chromate, but it does show a very huge multiferric behavior. Similarly, it was reported by Ghosh et al. That samarium chromate, this new compound, also shows a multiferric behavior, although the multiferric ferroelectric transition which is reported is more than even the first antiferroelectric transition, but they could have shown that it does show a multiferricity in this. So that's where this material becomes interesting, and something similar was reported very recently by G. Oliver et al. In scientific report. Next slide. So, as I told you, the very high neutron absorbing character of samarium compounds, particularly samarium chromate. The direct neutron scattering studies has not been done, and the confirmation that it really corresponds to gamma 4 phase, that is GX phase at high temperature and G2 phase at the GJ phase at low temperature. It is basically not directly probed by neutrons. It is only the G. Goretzky et al. Had done some very good sound velocity measurement studies and specific hit measurements, and they have shown long back in 1977 that this structure should correspond to a GX phase, and the spin-oriented phase must be gamma 2 phase, and it should be a second order phase transition. So far so good, but very recently in 2017, this M. Tripathi et al. Published and reporting that this gamma 4 and the spin-oriented phase is basically gamma 1. So basically they reported the gamma 4 to gamma 1 phase transition and a first order phase based on the neutron scattering study. Of course, they use high energy neutrons because to resolve the issue of absorption, they basically intelligently go back to the first slide. So they use high energy neutrons, and so next slide.
Dr. Rana?
Yes. Okay, so yes, sir.
Yeah, your time is up.
My time is finished.
Yeah.
Okay. Okay, so just only two slides. So we also prepared samples, and basically we just requested Pascal to check whether it's possible to do this experiment at WIS beamline, because that is a very high intensity beamline and high resolution beamline. So they conducted a room temperature, and we found very good data which can be refined. And the same was matching exactly with the X-ray diffraction result. So they told that the absorption of issue is not that much in this beamline. And next slide. So basically we conducted this experiment, temperature dependent experiment, and found that below 210 K the magnetic peaks are appearing, and there is across the spin oriented transition there was a change in the peak intensity. Next slide. So basically everything was refined when we used Jana for that. So basically next slide. So okay, so as you can see, we followed two approach on unconstrained and constrained. Unconstrained approach, so basically we allowed the ferromagnetic component also to refine, but as you can see there are a large amount of error when as compared to the absolute value of that component. So therefore we just made all of them 0, and the final structure which we could define. Next slide was the constrained one. So what we found that it is basically the gamma 2 phase. You can see here we just refined all the patterns for gamma 1, gamma 2, gamma 3, and gamma 4, because the others are not allowed because they give a B atom, chromium atom to be 0 moment. So that the 25 Kelvin and 1.5 Kelvin phase, which are supposed to be a spin-oriented phase, they are very nicely fitted with the gamma 2 phase or not by gamma 1 phase. Similarly, 90 Kelvin phase are of course getting fitted with the gamma phase only. And what this shows is the variation, temperature variation of the moments of the chromium and the moment of samarium. Samarium moments around high temperature are very small. Okay, next slide.
You please
so
conclude.
Okay, so this is showing the structure. So go to the last concluding slide. Yeah, so we concluded that the okay, I will just write the combined DC and magnetic field magnetization measurements in using time of flight to this beamline, that samarium chromate basically transformed from gamma 2 to gamma 4 phase and not gamma 1 phase. And in the case of this 25% of manganese and copper, we conclude that the cooperative joint error effect can be used to manipulate the structure in the spinels and to have a desired interaction of ion frustration in the compound. Thank you.
Thank you, Dr. Lala. I'm sorry that we are running late, so we'll not be able to take any questions. So thank you very much for joining.
Okay.
And let us thank all the speakers in this session. And now we break for tea, and then we'll be back by 3:45 Indian time. And I request the speakers in the following session to try to share the slides and then see whether it works everything well. Thank you. We'll see 3:45.
Can I share my slide?
Yes, you can share it, sir. Share it and check.
Okay.
Yes, sir.
Can you
It's
see?
coming good. Yes, we just check next slide.
Oh, that is okay. Yeah.
Yes, yes, it's coming. It's coming good.
Okay. Just a minute. Yeah.
Yeah, it's coming good only then. Thank you, sir.
Sir, can I check now?
Yeah, madam.
How to stop it? Okay.
Yeah, I will take it, sir.
Okay.
Madam, can you share it?
Yeah, sure.
You just press that share button. Yes, it's coming. Wait. Yeah, you just make it full screen.
Is it okay?
No, madam. Yeah, come. You just
Actually, how
press
do I
next slide.
minimize this thing? There is an active speaker video view.
Yeah, it just that is no need.
No.
Far end they will not get. Just
Okay.
PPT only it will come.
Okay.
That's on for you for your
For
purpose
me.
that window.
Oh, okay.
You
Thank
just
you.
press next slide. Yeah, it's
Is
coming
it
good.
coming? Okay.
Yes.
Yeah.
Just do it like this only, madam. Next.
Yeah.
In your presentation.
Yeah, sure, sir.
Thank you,
Now
madam.
I'll stop sharing.
Yeah, I will stop it that one.
Okay. Thanks a
You
lot.
just
Sir, can you do me one favor? Instead of telling me just 1 minute before, can you tell me 2 minutes in advance when the time is up?
in presentation time.
Yeah.
Okay, madam. I will tell to
Yeah. Thank you.
Sundarshan sir. Okay.
Yeah. Thanks.
Can I check my slide?
Yes, sir. You
Yeah.
just share that.
Share and then Microsoft Office.
Yes, sir.
Is it coming?
No, sir. Nirmala, madam.
Yes, sir.
Still your PPT is showing here.
No, this is not mine. It was there before mine.
Before my.
Yeah.
This is mine. How to stop it?
I think Ravi sir,
How to stop it?
you just exit that in upside stop sharing options is there.
Okay.
Actually, if you move your cursor on the top bar, you will see the stop sharing button. Just move it horizontally in the top portion.
Okay, yeah. Okay, so okay, I can.
Yeah, you just make it full screen, sir.
Okay, let me.
Yes, it's coming, sir.
It's coming now. Okay, fine.
Yes, yes.
I'm stopping. Yeah, thank you. Thank you very much.
Yeah, this one again, it's coming, Ravi sirs.
Yeah, Ravi sir. Yeah, it's.
Ravi sir, your PPT again is sharing.
I cannot see uh, I can get again option for the share content and all the thing. I'm not sure from where it is sharing.
You just share again and you can stop it, sir. You can try it like that.
Okay.
Okay, you just now you can stop the screen share.
Yeah. Okay. Again, it is coming.
You just close this PPT in somewhere you open in your system.
Okay.
Can you try to exit meeting and again join, sir? It's
I
possible.
already done that.
Okay.
Hello. Hello.
Hello, sir.
I cannot remove it even and it is not open like I open from file. Somehow it is stuck like whenever I am connecting it again, it is coming.
Can you make it leave meeting and again join?
I done that already.
Can you try it again, sir?
I don't know from where it is coming. Sorry?
Still it's coming, sir.
Yeah, I don't know from where it is picking up. You can say it like I can.
He has to stop now.
Yeah. Stop sharing is there, sir. Here.
Yeah.
Yeah. Yeah. See, still it's there.
Yeah. So some.
Please disconnect fully from this link.
I like whenever I'm opening. Okay, I'm moving to different computers. So just a minute.
Yeah, just cross that red button.
Any other computer you are using, sir?
Oh. Sundar, I can share also. It's showing. Try sharing. Done. Oh. Not loading. Yeah. Done.
Yes.
So, welcome back. So, now we have Professor Sundarasan from JNCASR Bangalore, as all of us knows him very well. So, Professor Sundarasan, please start, and we have 13 minutes plus 2 minutes for discussion.
Okay, thank you, Professor Kanska. So the title of my talk is Unconventional Spin Density Wave in Doubly Ordered Perovskite. So I think before that, I must tell you what is conventional spin density wave. And before that, I must tell you that what is the motivation to study this doubly ordered perovskite. So this is what I'm going to tell you, that before that, I must acknowledge the contributions. So of course, Ravi Shankar is a student who worked on this problem. And before that, Chandan was working on this doubly ordered perovskite. And we have a strong collaboration, and of course, the data from ISIS, Fabio, and then Pascal. And we published this data last year, 2020. And then our Mike Wangbo, I think many of us we know, is a theoretician, and he found that our results are very interesting, and he want to calculate and see why this structure, this unconventional spin density wave occurs in this material. And in fact, he did completed the work within 2 months, and within 3 months, we published the paper also in inorganic chemistry. So he is a very, very interesting person. So this is my plan of my talk. Very briefly introduce multiferroics and chemical ordering induced electric polarization, and then the polar doubly ordered perovskites, and then I will come to the unconventional. So we all know that multiferroics is a combination of both ferromagnetism and ferroelectricity, or in general magnetism and ferroelectricity. And people are looking for very interesting applications like a 4-state logic memory systems by controlling, for example, electric polarization by magnetic field or vice versa. So these are the possible, what you can see here, possible application envisaged for multiferroic materials. Okay, so now briefly I want to tell you that whatever known materials as of today, there are 2 kinds you can classify. One is based on the type 1 multiferroics here, and that is based on that you have ferroelectricity comes from certain ion and magnetism coming from the other one in the structure, and they give rise to the multiferroic properties. So this can come from the lone pair effect, the ferroelectricity, or a structural distortion or charge ordering. The type 2 materials or magnetic materials, in which the magnetic ordering itself breaks the inversion symmetry, which is very interesting aspect, and so that we can control the ferroelectric polarization by applied magnetic field. So, and for application purpose, this spin-driven ferroelectricity is very interesting. And as we know that it is driven by spin ordering, so it's important to do neutron diffraction to understand the magnetic spin structure and the symmetry of the spin structure, whether it breaks the inversion symmetry or not, or the polar or non-polar, or it can be simply a non-centrosymmetric but non-polar. This kind of things are possible. So we have been working on inversion symmetry breaking by chemical ordering, which means it can be either cation ordering, include charge ordering, or a same kind of cation in different chemical environment, like octahedra versus tetrahedra and so on. So they can be arranged in a regular different manners in the structure. Or so this kind of things can lead to a different kind of polar structure, and that's different from typical ferroelectric or conventional ferroelectric material. Most of the conventional ferroelectric material like barium titanate or lead titanate or PZT can be switched by applying electric field by changing the direction of electric field. But in this kind of materials where inversion symmetry is broken by chemical ordering, this material remains pyroelectric. That means you cannot switch the polarization because the polar state is stabilized by the chemical ordering right at the formation temperature of the materials. So the typical example is the zinc blende structure. So we know that this is a diamond structure, and you can replace it by zinc and sulfur, and you can break the inversion symmetry here. So it becomes non-centrosymmetric. So this is the textbook example, but we know that there are corundum derived structures. So corundum structure L2O3 is centrosymmetric, but we can have various type of this kind of ordering, a simple ordering or double ordering. They can give rise to a kind of ordered ilmenite structure or centrosymmetric ilmenite structure. So they can be polar or non-polar, like that LiNbO3 structure or nickel 3TO3 type, which is R3 space group, which is polar again. So you can derive like different kind of ordering pattern. So you can get this kind of polar structure. So one example, what we have done is discovered in our lab is the family of askinite structure, which was not known before, but of course this askinite is mineral is known. But we derived this things, which means it is an ordered askinite, which is dysprosium and Fe3 plus and tungsten 6 plus. They ordered at this so-called, let us say B site, but this is not perovskite structure, it is askinite. So you can see this is the structure, which is the space group is PNA21, which is polar, and the askinite structure is PNMA, which is centrosymmetric. So this structure is derived by just ordering Fe3 plus and tungsten 6 plus in this. So that breaks the inversion symmetry and gives you a polar structure. That means right at the room temperature it is polar, even at the formation temperature, below the formation temperature it is polar. So it remains pyroelectric, so you cannot switch the polarization, but below the magnetic ordering temperature of Fe, it's very interesting. You can see a change in polarization, which can be controlled by applied magnetic field. So in order to understand the origin of polarization, we did a magnetic structure determination in ILL. This was the previous result, and we published. And it's a very unusual non-collinear but commensurate structure. And either this polarization can add to existing high temperature polarization, or it can independently give polarization along the A and C direction. So coming to this perovskite structure, because the current topic is the doubly ordered perovskite structure. So simple perovskite structure, we know that is a PM3M space group, and we also know about the octaorbital distortion or rotation by the tolerance factor. Tolerance factor controls the ionic bond mismatch, and that can control the various octaorbital distortion. We can get large number of perovskite, distorted perovskite structure in various space groups, but most of them are centrosymmetric, except barium titanate or lead titanate or bismuth ferrite. So where you can clearly see the second order Ionteller effect associated with the titanium or the bismuth ion, bismuth 3+, which is associated with the lone pair electrons. But not all lone pairs gives rise to ferroelectricity. We should remember that. So except that, all the distortion of the perovskite structure are centrosymmetric. We can make ordered perovskite, like a B-site ordered perovskite, that means a rock salt ordering or a columnar ordering, but both of them gives you again centrosymmetric structure. And you can have this kind of layered ordering of the A cation, okay, or B cation. For example, copper and zinc here orders very rare in this kind of ordering in the B site. But we can also make it ordered at the A site. That means you can have ordering at the A site, you can order at the B site. So this kind of ordering pattern, that's why we call doubly ordered, which means A site and B site are ordered. Again, you can have different kind of patterns. So one is a layered ordering. So the A site is layered order, and the B sites are rock salt order. Okay, and the A site can be columnar ordering, or the A site can be rock salt. So in all these things, the B site is a rock salt ordered structure. But again, all these structures still it is centrosymmetric. But you can make it non-centrosymmetric and polar by what you can do is you can make a smaller ionic substitution at the A site, okay, and like sodium, for example, potassium or rare earth like this, and then you can make an octaorbital distortion, and you can combine different non-polar modes to at least these two non-polar modes and make a polar mode. Okay, so because of the short of time, so I will not go into details about it, but you can see this about these polar modes in this paper. So what we have done, so we made sodium yttrium. So this is not going away. So sodium yttrium, and then manganese, cobalt, and nickel, and then tungsten. So you can see that all these materials can be stabilized only under high pressure because of the low tolerance factor. And it gives you highly distorted octahedra, as you can see tungsten O6 and manganese O6 here. And particularly tungsten O6 and O7, you can see the difference in bond length. So 1.89 and 2.13. So this because of the second order Ionteller distortion, and this is coming close to the sodium ion, and still it will not give you polarization, but the polarization comes from the opposite shift of the sodium ion and then the rare earth ions here, and they are not equal, so you get finite polarization in this material. But again, in the paramagnetic state, they remain pyroelectric, they are not ferroelectric. Okay, so for example, sodium, yttrium, nickel, and tungsten O6, you can see this is magnetic ordering at low temperature. Left side is the magnetization, and then the right side is the heat capacity. Confirming the magnetic ordering, there is a small shoulder here, another magnetic structure transition here, and you can see the dielectric anomaly occurs at the transition temperature. And I'm running out of time, so I think I should. You can see the polarization appears at Tn, that means a change in polarization, and this is confirmed by pyroelectric current and so on. So we have done neutron diffraction to understand the magnetic structure at 20 Kelvin and 1.5 Kelvin. So 1.5 Kelvin, this is the WIS data, and you can see the magnetic structure is commensurate at this temperature, and the magnetic moment components are mx, my are given here. And you can fit the evolution of magnetic moment with this mean field theory, and you can get this beta equal to 0.17. And at 20 Kelvin, the magnetic structure is different. It's not commensurate, it is incommensurate, and the K vector is 0.47409. And that's what we see. This is a spin density wave. Unusual spin density wave just below Tn. At very low temperature, it transforms to a commensurate structure. Okay, so this is incommensurate structure, and you have the magnetic moment here. So you can see the spins which are antiferromagnetically aligned. Okay, but this is a spin density wave propagating along this direction. So now I must tell you that what is conventional spin density wave. Spin density waves or this kind of spin waves transversing in this direction. For example, transverse spin density wave, which is a combination of cycloidal structure. A cycloidal spin structure, for example, it's rotating in this plane, and there is another possibility it can rotate in opposite direction. So you have two chiral structures. So these two structures are chiral. So this can give you polarization. Whereas this combination, they have the same energy. So that gives rise to this kind of transverse spin density wave. That means the spin direction is perpendicular to this, the propagation direction of the spin density wave. But in the longitudinal spin density wave, the spin direction as well as the you can see the propagation direction are in the same. Again, this is a combination of the two chiral cycloids, and normally spin density occurs below the Tn when you have a frustrated system, mildly frustrated system, and then it transforms to collinear structure at low temperature via one of these cycloidal structure. So, but in different system it occurs differently. So our Mike Wangbo did the calculation to understand why it takes this kind of antiferromagnetic spin density wave. So you can see that in the conventional spin density wave, each half is ferromagnetic. So one half is ferromagnetic and next half is ferromagnetic. But in our case, each half is antiferromagnetic. That's why it is unconventional, very unusual. So he tried to calculate using the various exchange parameters through TFT, incorporating the U values, and he has taken 3, 4, and 5 EV, but all of them give a similar trend. So we have taken the 4 EV and got all these values, and then get the ground state structure here. And this is what we see, that the antiferromagnetic chain is this one, and you can have a cycloidal of antiferromagnetic cycloidal. Okay, so that means the spins you have in neighboring spins are antiferromagnetically coupled, but they make an angle like in cycloidal spin. So cycloids of opposite chirality, that gives rise to antiferromagnetic spin density wave that we observe in this system. I'm sorry that I could not explain much because of the time, but so there is a conventional spin density wave. We have a ferromagnetic in one part, and another part is down, but it is also ferromagnetic. But here, each half we have antiferromagnetism. That's why it is unconventional ferromagnetism. So again, the spin structures along the different directions, when you take the Kc equal to 0.5 instead of 0.49, you can see the antiferromagnetic spin structure along the C direction. But along 101 direction, you can have a ferromagnetic spin wave kind of structures here. So the conclusion, I would like to conclude that NaY NiWO6 pyroelectric in the ferromagnetic state, it shows switchable polarization below Tn 21 Kelvin. It undergoes an unconventional antiferromagnetic spin density wave below Tn. At low temperature, it goes to commensurate spin structure. And since all these spin structures are centrosymmetric, the change in polarization should occur, probably due to magnetoelastic effect in these materials. So thank you.
Thank you, Professor Sundararajan. So let's see if we have any questions. No. Thank you. Okay. In this hall, I have one question. So it's more like it's very simple question, like, right? Yeah. So you showed like doubly ordered perovskite, like in different direction, layer or columnar. But in halide perovskite, like we say, like basically double perovskite.
Yeah.
Is the same thing?
This is A site order also order, B site also order.
Okay.
But most of these double perovskites are only B site is order.
B site is order. Okay.
But here A site also order.
Okay.
And A site also can order in different ways.
But formula wise, it looks similar. Like
no, you write when you write. Otherwise, you will write 0.5, 0.5.
Okay.
Na 0.5, yttrium 0.5.
Okay.
Which means it disorder.
Okay.
But when you write Na and yttrium, it is ordered.
Ordered, yeah.
Yeah.
So
And then O6.
okay. But that means whenever we have 0.5, that means it is
That means
disordered.
it disordered.
So I'm saying without doping.
Yes.
Without doping, say.
Yeah, without doping also it can be disordered. For example,
Can be disordered.
Yeah, it can be disordered.
Okay. So that time it's not ordered perovskite.
It's not ordered perovskite. Yeah. They should occupy different crystallographic sites.
Okay, sure. Thank you.
For joining this session to my talk. So next talk will be given by Professor Nirmala from IIT Madras. So I will not spend much time. So she is going to talk on the title is there, unconventional superconductivity. Okay.
Sir, no.
Towards understanding the magnetic ground state of CuL2O4. Please go ahead.
Hello.
Yes, please
Am
go
I
ahead.
audible?
Yes.
Okay. Is it full screen?
Not. No.
Okay. Now?
Yeah, now it's okay.
Okay. Thank you very much. So first, good morning, good afternoon, and good evening to all the audience here. So I would like to start by thanking the organizers for giving us this opportunity to share this particular work in this meeting. So in this work, we primarily try to understand the magnetic ground state of normal spinel copper aluminum 2O4. So this work was potentially, actually, I started doing this work when I was a postdoc with Professor Jagan Park in Korea. So we continued to work on this, and the primary collaborators are Dr. Hambum Cho, and I already mentioned Professor Park from Seoul National University, and our collaborators from ISIS RAL facility are Dr. Adroja and Dr. Peter Baker. So let me start from the very beginning. So spinels are materials having this general chemical formula AB2X4, where A ions are usually the divalent cations such as magnesium, iron, etc. And B ions are trivalent cations, examples aluminum, iron again. And X ions, anions, these are oxygen, or these could be sulfur or selenium. So the well-known spinel, a normal spinel, the first one that is known to us, the naturally occurring one, is the magnesium aluminum 2O4. The structure is actually, you can describe it like this. The oxygen ions form a close packed cubic structure, leaving out some voids in which the smaller A ions and B ions go and reside. So what kinds of voids are available? You have tetrahedral voids and octahedral voids. 8 tetrahedral voids and 16 octahedral voids per unit cell are available. So this is the basic structure. The other naturally occurring spinels are, for example, the ruby is another spinel material. And we talked about A and B sites in this. So how A and B site ions go and occupy their sites will help us classify this further into normal and inverse spinels. So normal spinel is what I have described in the previous slide with an example of magnesium aluminum 2O4. And in inverse spinel, we have some of the B ions go and sitting at the A site and vice versa. So you have some site mixing. A good example that all of us know from our literature is that of magnetite, Fe3O4, which you can write as Fe2O4. You have iron 3 plus at A site, you have iron 3 plus and iron 2 plus in the B site. And therefore, if the coupling between the two sublattices is anti-parallel, you are going to have uncompensated 4-Bohr magneton from the B sublattice, which makes this as a ferrimagnet. So this is a first known example of a ferrimagnet, but that comes from this nature of mixing, site mixing, or it's one example for the inverse spinel structure materials. So For this, we define a parameter called inversion parameter I. I is nothing but the number of B ions that go and reside in the A site. Okay, so if I is equal to 0, you have perfectly normal spinel, and if I value lies between 0 to 2/3, you have largely normal spinel, and if I is equal to 1, you have perfectly inverse spinel, and so on. And so how do we understand this spinel structure? Now I would concentrate on what is called normal spinel. Your A ions completely go and sit A site, and B ions go and sit completely in B site. Okay, so we should now try to understand the magnetism of this normal spinels. So you can think of this AB2O4 as sum of two sublattices, one made of purely A ions that forms diamond cubic structure, and another made of completely B ions that forms a well-known pyrochlore structure. Okay, and now we are trying to see the first frustration effects in a normal spinel where the magnetic ion sits at the A site. Okay, so that's somewhat tricky in the sense that we all easily can connect to frustration in a B site magnetic ion spinel. Why? Because we just listened to Professor Lalla already that in a pyrochlore lattice, which you can think of as a 3D variant of a 2D Kagome lattice, right? So here you have corner sharing tetrahedra, and if the nearest neighbor interactions are antiferromagnetic, you can't establish equal number of pairwise interactions nulling each other. Therefore, you have to have frustration as a result. But if magnetic ions are residing in A site, you have a diamond cubic lattice. And what is a diamond cubic lattice? A diamond cubic lattice from our early solid state physics is nothing but two interpenetrating FCC lattices, right? So these are displaced from each other along the body diagonal by 1/4, 1/4, 1/4, right? So if the nearest neighbor interaction is antiferromagnetic, you should have equal and opposite moments. Therefore, that should result in collinear antiferromagnetism, not really in frustration. But that is not something that always happens. This is the theoretical work by McDougall, who proves that collinear antiferromagnetism as a result if you consider only the interactions between the nearest neighbor A ions. Okay, so that should result in collinear antiferromagnetism. However, how these A ions, nearest neighbor ions, are connected. I think we should go to the next slide, where you can see that J1, the exchange strength between the nearest neighbor A ions, this A and A are actually connected via BO pathway, right? So actually the typical bond lengths that we have between two nearest neighbor A ions is something of the order of 3.54 angstrom. So therefore, this interaction is somewhat ineffective. Therefore, one has to consider the higher order interactions, and therefore J2, for example, the next nearest neighbor interaction could come into picture. So this work by Bergman et al. Shows that if J2 by J1 ratio, depending on that value, the magnetic ground state is decided in the diamond cubic lattice. For example, if the ratio J2 by J1 is between 0 to 1/8, then you will have collinear antiferromagnetism in that material. Whereas if J2 by J1 is more than 1/8, you can have large ground state degeneracy resulting in kind of, large variety of ground states, including spin spirals and spin liquids. All kinds of exotic states are predicted. So that's what gave the primary interest to study the normal A site spinels, where you have the magnetic ions in the A site. So again, to summarize, what we are saying is, in addition to the nearest neighbor interaction, we are considering next nearest neighbor and possibly the higher order interactions as well. Okay, so these pathways are shown here in this view graph that is taken from this work. So in the literature, it is already known that cobalt aluminum 204 and iron aluminum 204 show no long range order, and these exhibit spin glass like ground states or spin liquid like ground states. And manganese aluminum 204 is material which shows this long range antiferromagnetic order. Actually here J2 by J1 is typically 0.09. So it shows a Néel temperature of 42 Kelvin, below which you see long-range antiferromagnetism. This is confirmed by neutron diffraction. Whereas in the case of cobalt aluminum 204, one finds that J2 by J1 is very close to this 1/8 value, 0.125 or something. So it's exactly in the critical point, and therefore one has glass-like ground state. And the literature on copper aluminum 204 was very weak and feeble, and magnetism was remaining not very well reported. That gave us the motivation to study this spin half spinel, namely copper aluminum 204, where copper is in 2+ state. That gives you a quantum spin half in your material. And what we find is this copper aluminum 204 is largely normal spinel. Okay, so you have some site inversion of something like I value varying between 0.2 to 0.3 depending on your synthesis. It's extremely tricky to reduce this inversion parameter. However, it is in the largely normal spinel window, and it is cubic FD 3 bar M space group, and this is a typical X-ray diffraction pattern that I have shown. So actually the inversion parameter is calculated as a function of temperature in an in situ measurement by this group O'Neill et al. So there they are showing how this I value varies as a function of temperature. Okay. So we went on to study magnetism. So low field magnetization data actually shows here a cusp in the magnetization in low fields of something like 20 oersted. So this low temperature peak, this maximum value is something like 2.3 Kelvin. And this peak vanishes when you apply higher applied fields. And the paramagnetic susceptibility follows Curie-Weiss law, but the Curie-Weiss temperature that you get from the FIT is having a very large negative value as you would get for a frustrated material. And the mu effective value is slightly more than the spin half value, the spin only value of copper plus ion. Okay, the spin only value will be something like 1.78. And this shows you actually the low temperature measurement, clearly showing the cusp that is seen around 2 Kelvin. So the question is, what is the nature of this cusp, or does the material orders? What we here list are the frustration parameter. The frustration parameter is defined as the ratio of the Curie-Weiss temperature divided by this critical temperature or the cusp temperature. So in this case, T star is 2.3 Kelvin, as I mentioned. So what you see here is for other spinels like cobalt aluminum 204, iron aluminum 204, this frustration parameter is something like 22 or 11. And in the case of manganese aluminate, which is a long-range order antiferromagnet, this is fairly a small number. Whenever frustration parameter is more than 10, it's considered to be a frustrated system. You can again see here the map of F as a function of the spin. This is manganese, which is long-range ordered material. This is spin S is equal to 2 system, the iron aluminate. This is 3/2 system, and nickel aluminate is not studied because it's not a largely normal spinel. It rather forms as an inverse spinel, so we'll leave that out from our discussion. This is our copper aluminum 204, where you see really the largest value for the frustration parameter. Okay, so that led us to study the AC magnetic susceptibility, because we want to see whether the system is glass-like. So what we see here is that the cusp is again featuring here at low temperatures around 2 Kelvin. And with increasing frequency, this cusp is shifting to the right. Okay, so the arrow is towards the increasing frequency. And what I show here in the right-hand side panel is the M versus H. This is the DC magnetization. Again, you find that the lowest measured temperature, namely 0.6 Kelvin, one gets only roughly 0.12 Bohr magneton, which is fairly very, very small. It's more than 50% smaller than the iron aluminate and cobalt aluminate magnetization values at low temperatures in the same field of 5 Tesla. So given this, we have also done the time difference of magnetization.
Professor Raghunath?
Yeah.
Your time is up. You can take 1 minute maybe.
Okay. So here we see the logarithmic dependence here. This is again a signature of the canonical spin glass. So the questions that we had is whether the system is spin glass-like. So the heat capacity shows again that cusp, and in fields, the cusp shifts to right, okay, as you would expect for a ferromagnet rather. If it is a canonical spin glass, Milos says you have to have a linear temperature dependence that is not seen. However, you see some kind of a T-square dependence as one has seen in the cobalt and iron cases. And we have subtracted the phonon black zinc data and obtained the magnetic entropy. And we find that we have indeed large 0-point entropy in the system. So again, all these observations point to a canonical spin glass-like behavior in the system. One additional data from the high-resolution neutron diffraction. This also shows a lack of long-range magnetic order down to 0.4 Kelvin, and there is no structural transition down to 0.4 Kelvin in spite of the fact the copper 2+ is ion-tender ion. So all these points motivated us to study muon's spin relaxation. The question in front of us is whether the spin half copper aluminum 2O4 is a spin glass, and how about the spin dynamics of Cu2+ in the system at low temperatures. So the muon spin relaxation data, this is the zero field data that is shown here in this view graph. So what we see here is from 15K down to 3K, you have a decay, Gaussian-like decay, that is fitted to a dynamic Gaussian Kubo-Toyabe function. I have not shown this function. It has two parts, a static term and a dynamic term. Dynamic term is exponentially decaying, signifying the paramagnetic spin fluctuations. And the static term is related to the localized moments, the nuclear dipole moments. So what we see is the lack of oscillating feature that you saw in Dr. Adroja's slide, which means that there is no long range order down to 1.4 Kelvin. Okay, that's one primary observation from the zero field data. And from the field dependence data, so here we record the muon depolarization data as a function of increasing longitudinal field from 0 to something like 3000 Weierstrass. We have done this experiment at the lowest temperature, that is below the T cusp, which is 1.4 Kelvin. And what we see is the dynamic spin fluctuations are significant, and one actually sees a very weak field dependence below 1.4 Kelvin for the decay rates. The lambda1, lambda2 values actually saturate, which means that the ground state is still dynamic and there are fluctuations present. And also the weak field dependence says that you have to apply larger field to decouple the muon spin from the local moments. So all this points to the fact that the ground state is not completely frozen as picturized by the bulk properties that we have seen before, but rather it has dynamic spin fluctuations present. So that's what we have understood by doing this muon spin relaxation study. So I would like to thank other collaborators in this work. There are a large number of collaborators. Dr. Iberson, we collaborated for HRTD. And we have also done some NMR experiments, which also reveals that there is no long range order down to 1.4K, but there are some short range interactions below this cusp point, namely 2 Kelvin. So thank you very much for your attention. We do thank DST Nano Mission for the support.
Thank you, Professor Nirmala. So,
and the results we have got are put in this.
Okay. So we don't have time for questions, but however, I would like to point out that CaAl2O4, we have shown the long-range antiparamagnetic ordering. I have just sent you the paper by email. It just appeared yesterday in PRB. So you can have a look and then we can discuss later.
Yeah, sure. Thank you. Thank you.
Thank you. Let's move on to the next talk. This will be given by Dr. Ravi Prakash Singh from ISER Bhopal. He is giving a talk on unconventional superconductivity in non-centrosymmetric superconductors. Dr. Ravi.
Thank you, sir. Thank you, sir, organizer, to giving me the opportunity to present my work. So I am going to summarize my last 10-year work on the non-centrosymmetric superconductor using mostly RAL facilities. So basically, so unconventional superconductors, like we define like superconductor where basically Cooper pair is not formed by mediated by phonon. Generally we term as a like unconventional superconductor, and these superconductors have basically a lot of applications. And this you can see that recent one is this twisted bilayer graphene, lanthanum hydride, and last year these hydrogen sulfide and hydrogen at high pressure. This is like one example. So our group also work on a class of superconductor, unconventional superconductor that we call non-centrosymmetric superconductor, because if you have like center of inversion is not present inside your crystal structure, so basically non-lattice potential generate a high spin antisymmetric spin orbital coupling. And if SOC is high, then your Fermi surface can break in two parts, spin up and spin down. So if you go by the conventional BCS theory, then there is like it is not, there is no chance to form the Cooper pair. But theory suggests like later, a lot of theoretical work suggests, but it will form as a like, because conventional superconductor can form either singlet or triplet. But here it can form in the spin singlet and spin triplet form. Like it is a mixed state, and this mixing ratio is governed by basically this spin orbital coupling. So we thought like if we can control the spin orbital coupling, so we can get basically spin triplet superconductor, and then because it is a very few are known and they have lot of application, high SC2 and all the thing. And if this scenario happens, then we are expecting this nodes in the superconducting gap, upper critical field exceeding the Pauli limiting field, and some of them displaying the time reversal symmetry breaking. So, and it was like hint of this triplet component was found in this cerium platinum DSI by Bauer in 2004. And after that, lot of work done, I think till now around 80 or 90 compound people search. But the problem is most of the non-centrosymmetric superconductor shows conventional S-wave behavior. So like I started work on this rhenium 6 X series. I choose this series because we want a high SOC material, and we just take like very heavy material for the looking the superconducting property and ground state, and it is formed in basically a cubic non structure. You can see that like it have a 58 atom per unit, and I mostly if you magnetization, it look like they are just like a normal type 2 superconductors, and we perform the lab based measurement. You can see that like even they are non-centrosymmetric. You can tell that they have like there are indication that like SC2 is very close to Pauli limiting field, and delta C by gamma TC basically BCS jump is little bit more compared to conventional, but we cannot say that it had the triplet component because even the conventional superconductor can show this kind of behavior. So basically then we thought to superconducting ground using the muon. So I don't want to cover now here because of its time is useful. And okay, I'm skipping this one. So basically, if you implant the muon inside the, so basically it will process and it will give you the local environment, what is the present inside the your system. So we perform this in superconductors. Only we perform the measurement in two modes. One we call transverse mode by magnetic perpendicular to the muon spin direction, and then they precess, and this give you basically idea about the how the vortex are arranged. From there you can calculate penetration depth, and then you can get the second experiment we perform, like it is a kind relaxation. Generally, we do in the zero field, like you implant the muon. If in superconducting ground state, if triplet superconductivity exists, so both the spin will up, so there will be a small magnetic field. So if you can see that, like one superconducting ground state, so you will see that there is a all these three compounds shows the signature of that magnetic signature in the superconducting ground state, and basically it clearly tells it have then we done this measurement in more detail. So transfers clearly so that it is basically similar behavior, but same time from this longitudinal RG field measurement, we able to find out clear signature of the transition temperature. So all these three compound shows signature of basically inside the connecting ground state, and basically because it was rarely observed phenomena, so we got in the like three compound compound. And one thing we observed, like because we are moving from zirconium, hafnium to titanium, there is no effect of SOC happening. Signal and everything is same. So like we conclude that like it have a complex magnetic state with a weak triplet component. So to clarify this one, we perform the same structure but a osmate for any signature of triplet component. So from there we concluded, and recently we done work, and it shows that like rhenium is playing the role in the for this frequent occurrence of the TRSB in the superconducting ground state. And to know about more about the superconducting ground state of non-centrosymmetric, so we look another compound, lanthanum 7, iridium 3, rhodium 3, and nickel 3. And this one is like here SC2 is very less compared to Pauli limiting field, and even gap value is not up to BCS. It is less than that. But surprisingly, these compound also is showing the basically kind of two gap behavior, and its behavior is a little bit different compared to other two members. So we have we are working on this sample, and it's to search further. Like sorry, I'm then we also synthesize a new non-centrosymmetric superconductor, that is zirconium 3 iridium, and here we found that SOC strength is almost same, but we are not able to see any signature of time reversal symmetry breaking. But from PSI, one group reported a signature of time reversal symmetry breaking because ISIS muon source cannot see very fast relaxation. So they are citing that like we are not able to see because here muon relaxing very fast. And we are working on more compound. So basically, we have done the measurement on these lanthanum platinum 3. But we found a new phenomena, like it have in the superconducting state, we able to find the signature of spin fluctuation. So we are like working on this problem. So see that if there is any relation between this symmetry breaking in the superconducting ground state and spin fluctuation. So this work is also going on. And whatever till now we got the knowledge, like for the rhenium system, whatever we got the knowledge from there, we found that rhenium is playing the role. So we done a measurement back with our Warwick collaborators, and we found that tantalum. When enhance the concentration, it is basically we able to see like enhancement in SC2, and it is showing the behavior. You can see here there is no any magnetic movement. Here it is showing. So lot of work. Our group is keep working on this one. So like this is basically, I cannot say conclusion because still we are working. So what we conclude, SOC role is there, and non-centrosymmetric superconductor can host some triplet component, but exact mechanism is not known. So we are working on different scenarios. So still we are working on different kind of superconductors. And so my association with the RAL is very old. Like in 2008, I wrote a proposal with Dr. DT Adroja during my PhD on HET and GEM. HET is now discontinued. And after that, from 2000 to 2012, I was postdoc in Warwick, and I was regular user of MuSR, HRPD, and GEM. And from 2012 onwards, from ISER Bhopal, I am using MuSR. And till now, nearly 22 papers. And because when I joined ISER Bhopal, there is no lab, nothing is there. So most of the student work is like initial work is focused on totally on MuSR. So we manage all the, before this Nano Mission, we manage the travel support from British High Commission, India, Ramanujan Fellowship Fund, and now we are getting support from Nano Mission. So like we are working with Dr. Adrian Hillier and Dr. Adroja. Deepak was my first PhD student. He was the international postdoc for 2 years in ISIS. Now he moved to PSI. And these 4 students is on the final stage. So I'm totally grateful for support this kind of experiment. Thank you. Thank you very much.
Any questions? Someone? No? So, Ravi, this the main your aim of non-centrosymmetric superconductor is to have a pure or it's a mixed symmetry.
Sir, it is a mixed way because we are getting both. We are getting basically it is largely we are able to see like if you S-wave behavior, but zero field measurement on few superconductor is showing the signature of triplet. So it is a truly mixed state. What is predicted by theory.
Okay. Okay. So thank you once again, Dr. Ravi, for interesting talk. Thank you very much. So let's move on to the next talk. This will be given by Dr. Aritra Banerjee from University of Calcutta. His title is Evidence of Improvement in Thermoelectric Parameters of N-type Bi2Te3 Graphite Nanocomposite.
So, I'm Aritra from the Department of Physics, University of Calcutta. I would like to thank the organizer for giving me an opportunity to present my talk here. Am I audible?
Yes.
Okay, thank you. Thank you. So the title of my talk, Evidence of Improvement in the Thermoelectric Parameters of N-type Bi2Te3 Graphite Nanocomposite. So actually the relevance of this talk in this particular platform is that we obtained some interesting features in the improvement in the thermoelectric parameters with graphite nanocomposite, and then we would like to probe the phonon density of state, the role of directly how it is modifying graphite. So that's why we wrote a proposal, and it was finally we carried out the experiment at Rutherford lab. It is on the inelastic neutron scattering. So I will also try to cover that. So very recently, just last month, we published this paper in Journal of Applied Physics, and so before going in details, it is the very basic introduction to thermoelectric materials, which are special type of semiconductors that have the ability to convert thermal energy to electrical energy and vice versa. So it could be a solution to today's energy challenge because it could convert waste heat into electricity. So I'm not going in the details, it has some advantage, and the main problem with this is the use is limited by the low efficiency of a thermoelectric material. So efficiency of thermoelectric material is can expressed by this term ZT, so sigma a square by kappa, where sigma is electrical conductivity, this is thermal power, S is thermal power, and kappa is the thermal conductivity, total thermal conductivity. So we need high power factor and low thermal conductivity. So ideal thermoelectric material should desire high ZT, that is high Seebeck coefficient, which is high in crystalline semiconductor, and high electrical conductivity, which is high in crystalline metal, and low glass thermal conductivity, which is low in glass. So actually, if we see the relation of these parameters with the carrier concentration, we see that they are differently related with carrier concentration. So I am not going in the details, but here for S it is inversely proportional, where for sigma it is directly proportional, and kappa thermal conductivity has two part, kappa L, and that is lattice thermal conductivity, and this is electron thermal conductivity, which is related to sigma by Yd and Franz law. Again, N is here proportional. So this is the problem, is that here all these material parameter, important material parameter S, sigma, and kappa E are interrelated, and in a good thermoelectric material we should have the goodness of a semiconductor, a good metal, and a good glass. So all should combine in a good thermoelectric material. But the main problem here is that, as I told, these are interrelated. S, kappa, kappa E, and sigma are interrelated, and the only independent parameter here is lattice or phonon thermal conductivity. That is, phonon plays a significant role in this part. And as the central idea is to maximize phonon scattering relative to the carrier scattering, that is the decoupling of phonon and electron transport. As Konisko gave a nice introduction of going to an office by a car, and if the car is damaged by the phonon, what will happen to the car? So like that, we also want that phonon gets destructed, so phonons get some obstruction. So this is the central idea. So maximize phonon scattering relative to the carrier scattering, and for that a solution might be a nano composite system. So nano composite system, actually, when we imposed or we embed some second phase, disperse some second phase in the matrix of the crystalline sample, then we get some create some defect, say point defects, some dislocation like grain boundary like 2D defects, or dislocation like 1D defects. So then these defects scatter the phonons of different wavelength differently. So I'm not going in the details. So the thing is that, so this gives some energy filtering effect, and finally we get some betterment in the thermoelectric property. We are supposed to get some betterment in the thermoelectric property. So we synthesize. Our focus is to Bi2Te3 for this work. Bi2Te3, which is a well-known P-type and N-type thermoelectric material. So we here synthesized N-type thermoelectric Bi2Te3, and then added graphite as a second phase. But why graphite? Because carbon-based materials are reported to provide phonon blocking. So carrier mobility is high. So we want, when a carrier mobility is high in the graphite, and the thermal property of graphite is highly anisotropic. So that phonon moves well in the one direction, other direction is bad. So sample preparation are not going the details. We pristine samples we synthesize by melting method or solid state reaction method. Then we prepare the composite samples by ball milling method. I'm not going in the details. We characterize the sample at powder diffraction, the structural characterization, and then we carried out Rietveld refinement. We identified the graphite through Raman spectroscopic studies, and then for resistivity measurement, thermal power we carried out at our lab. Then temperature dependent thermal conductivity we carried out. We don't have this measurement facility. We carried out with my collaborator, and Hall coefficient we measure at UGC DAE center. So we gave a talk this morning. So this inelastic neutron scattering experiment we carried out at Rutherford Appleton Lab using the Murray instrument, Murray spectrometer. And I'm not going into the details because I am not an expert in this field. So we when they carried out the experiment, and we get a help from Huneson and his group member in this experiment. So we carried out Rietveld refinement here. For 3 samples we carried out Rietveld refinement. So our analysis shows that Rietveld refinement is very good. So all the XRD peaks are peaks A with rhomboidal crystal structure of BI indicates the rhomboidal crystal structure of Bi2T3 phase having R3 bar space group, but the XRD pattern reveals that the samples are single phase in nature with no additional peaks due to graphite. But the main reason, so we impose graphite, but the graphite is not observed. So the main reason may be the amount of graphite is quite small and beyond the detection limit of XRD. So variation. So now we get some indirect evidence from while estimating the grain size and strain. From so for typical free planes, we see the grain size. This is we represented here for 3 planes. This is a general picture for all the different planes. So we see that grain size is decreasing with incorporation of graphite, and then so that is graphite incorporation inhibits the grain growth, whereas the strain increases. This suggests that graphite particles indirectly suggests that graphite particles are embedded in the matrix and present as a separate phase. Now we get the direct evidence of graphite from Raman spectroscopy, where this shows that this is a pristine sample Bi2T3, where there is no, this is the graphitic phase, this is the phonon modes Raman of Bi2T3, but here we don't show for the pristine sample any graphite phase, but for these 2.05% composite samples we get clearly the graphite phases. So I'm not going in the details. So now the thermal conductivity, most important thermolytic parameter. So here we this is the plot. This red one is the pristine sample, and the composite sample. We see that for the composite samples, these thermal conductivity has decreased, particularly room temperature has decreased. Overall, the thermal conductivity has decreased with graphite addition. We calculated kappa E from resistivity data, and finally kappa L from, that is phonon thermal conductivity or lattice thermal conductivity, and which follows the same trend as that of the main the total thermal conductivity. Actually, this electron thermal conductivity is very small amount contributes in the total thermal conductivity. The most contribution of total thermal conductivity comes from the lattice thermal conductivity, and this shows that it is following the same trend, and we get a 17% decrease in the room temperature lattice thermal conductivity, which is a very good amount of decrease with this graphite addition. So this interface, actually, in order to give an explanation to us this, so this interesting result, we could suppose that the interface performs as energy filtering source that preferentially scatter phonons and suppress the transport of mid and long wavelength phonons. This tends to reduce the lattice contribution to kappa, that is kappa L is reduced substantially. Now to probe it more details, we carried out the phonon density of state. We try to see the effect of graphite in the phonon density of state and of the sample. So we carried out inelastic neutron scattering experiment. This is a low energy spectra obtained at 5 Kelvin with inelastic neutron scattering experiment. We see that clear deviation in this region. Hello? We see that there is clear deviation in this region. So this is a low energy peak itself, low energy region. So in this region, 2 to 4 MeV region which corresponds to both optical and acoustic phonon modes. There is some clear deviation between the pristine sample and the highest graphite dose samples. And there is no signature of graphite in this region. So graphite, this is a pure graphitic line. So this shows no peak in this region. So to give a more greater observation, we carried out the DESY plot. We plotted the DESY plot, and where density of state by E square is plotted against the energy, and we see that there is confirms the introduction of graphite in the matrix is indeed modifying the density, underlying phonon density of state of Bi to T3. This is the peak that gives rise to this one, this region. So that's why we could say that the Bi to T3 is indeed the phonon density of state of Bi to T3 is indeed modified by graphite addition, and which is reflected in our thermal conductivity and overall thermoelectric power data. So this is thermal power of measurement data, which shows that the Seebeck coefficient is negative. That is the sample hour is n-type in nature. So the Seebeck coefficient increases in this is the pristine sample. So Seebeck coefficient increases throughout the temperature range in the composite samples. So graphite at the grain boundary act as potential barrier, which filters the electron energy distribution and block the low energy electron. So this is the resistivity curve, which also decreases in the composite samples. So decrease in resistivity corroborates with the carrier concentration data. So now we plot the ZT value. So though ZT value is not very high in the samples, but the ZT, we see that ZT increases by 40 times in this in this sample, that is our pristine sample at room temperature. ZT increases as compared to the pristine sample. This is the highest graphite samples, increases by around 40 times. So this is a huge increase in the graphite in the ZT value in the sample. So I would like to conclude. So both Seebeck and electrical conductivity increases for the nanocomposite samples. Large decrease is observed in lattice thermal conductivity for nanocomposite samples. So introduction of graphite into the matrix modifies the Bi to T3 phonon density of state. ZT increases by around 40 times for Bi to T3 graphite composite as compared to the pristine Bi to T3. So my group members, my colleague Subarno is my PhD student who just submitted his thesis yesterday. Pintu Sinha myself to carry out the experiment, and these are two young members of our group. And my collaborators, actually, I would like to thank JNCASR also for inviting me and UNESCO for this India-UK conference. Hello? India-UK conference in, I think, 2018, where this collaboration is there. So Professor Powell from Reading University attended the conference, and it was a nice interaction which finally led to this collaboration. And David Voneson from ISIS and Tanzania, these are the samples and data help us in data analysis. My collaborators from Moscow State University and IGCAR for my Raman spectroscopic measurement. So Souvik from UCD Kolkata for magnetic transport property, and Apurvo who helped us in this Rietveld refinement of our samples. So I acknowledge JNCASR India for facilitating the experiments at the Rutherford Appleton Lab, and DST India for financial support, and UGCDA Consortium of Scientific Research Kolkata Center, and IUSC New Delhi for supporting my ongoing research work in the form of sanctioning projects. And thank you for your attention.
Thank you, Aritra. Is there any question online now here? I just want to ask you, what is the figure of merit for bismuth telluride just reported? Your value without it seems to be low, no?
Yeah, very low, very low. Actually, our density of the samples, we press the sample by hot press, but we do it by sending the samples to some place, and finally we get it. So the density of samples of the after hot pressing is around only 80%. So that's why otherwise there should have been at least the 10% to 20%, 20 times increase in the ZT value.
Yeah, but you cannot compare with the reported value without having a good density of your
Yeah,
sample.
exactly. So that's why we have been able to publish only in the Journal of Applied Physics. Otherwise, with this quality of data, we should have been gone in much more a paper.
Okay. So thank you, Aritra, for a nice talk.
Thank you.
Let's move on to the next last talk. This will be given by Dr. Subham Majumdar from IACS. He is going to talk on neutron and muon studies in magnetic shape memory alloys. Subham?
Yes, I'm here. Can you hear me?
Yes, yes. Make it full screen and done.
Yeah, I made it full screen. Okay, fine. Yeah.
Go ahead. Yeah.
Very good afternoon. And the title of my talk is Neutron and Muon Studies in Magnetic Shape Memory Alloys. Actually, there is a subtitle of the topic, so which is, are ferromagnetic shape memory alloys really ferromagnetic? So this is a very intriguing question, and for a long time, people have actually made conjecture about their true magnetic state. And in this particular work, we took neutron diffraction and muon spin rotation technique to understand the magnetic state of the material. And so the question comes, what is a ferromagnetic shape memory alloys? So they are basically ferromagnetic materials, and they undergo a martensitic transition, both as a function of temperature and can be also as a magnetic field. So at high temperature, this ferromagnetic shape memory alloys, they're basically metallic alloys, remain paramagnetic. Okay, and they have magnetic ions in there. And when the temperature is lowered, they undergo some kind of a ferromagnetic ordering. So the high temperature phase, we call it austenite. And when you cool it down below a certain TC, it becomes ordered ferromagnetically. And on further lowering of temperature, there's a structural transition. And the structural transition drives the system from a different magnetic state. So the question is that whether they remain ferromagnetic or they become something else. So from simple magnetization data, people cannot conclude really what happens to these systems. And one important factor is that for ferromagnetic shape memory alloys, it should be ferromagnetic all the way. So its structural transition, that is a martensitic transition, should be less than the ferromagnetic tissue. So this FSMS actually can be deformed plastically. So what is the importance of this FSMS, ferromagnetic shape memory alloys? So there can be enormous deformation. So for example, you can deform it 10% with the application of a few Tesla of magnetic field. And most importantly, this shape can be recovered with a proper cycling of magnetic field and temperature. So they are quite useful. And they have immense importance in the field of magnetically controlled actuators, switches, memory devices. So there are different kinds of ferromagnetic shape memory alloys. So the most important of them are nickel manganese Z alloys, which are basically Heusler alloys. So here, to make them having shape memory effect, which is important, which is the to have its structural transition, we have to add little bit of excess manganese at the place of Z. So this is nickel to manganese Z, and you add a slightly more of manganese so that you can have a suitable structural transition. You can see in this graph, this is M versus T of a certain, and this is the hysteresis region where the structural transition takes place, and this is their TC. And so, so here there is a picture where by the application of a magnetic field, we are deforming a shape memory alloys, and we are getting back the shape again with the application of a force. So, so these are very important for mechanical devices, magnetomechanical devices. These materials are used, and people are actually using this for different magnetic switches and also for the generation of power. And so this is a picture where the shape is this magnetic field into strain versus magnetic field, where you can see that with the application of a magnetic field, you can create a large strain in the system, and which is about 10%. So in ordinary materials, the magnetic restriction is something like 0.1%. So here it is hugely large. And to understand the magnetic properties, so these have a lot of applications, but most importantly, they have also posed very interesting magnetic phase diagrams. So one alloy, which is one of the alloys, there are plenty of other alloys like that, which is nickel 2.04, manganese 1.4, and tin 0.56. And so you can see that this is plenty of different transitions. First up, one is TCA, where it becomes ferromagnetic. Then there is a martensitic transition, which is understandable from the hysteresis between the heating and cooling curve. And the magnetization drops here. And then there is another transition beyond which the magnetization starts to rise here again. So after the drop, it rises again. And in the zero field cool curve, there is another step-like anomaly, which is TB. So, and it's found that this below TB, the system shows some kind of a spin glass-like behavior. And it's not very clear what is happening below TB. And also below TB, it shows us some kind of a exchange bias effect. And so there are some open questions about it. So what is happening actually below this martensitic transition of this ferromagnetic alloy? So there are different ideas that there can be some incipient antiferromagnetic ordering, and order AFM phase, or a ferromagnetic state with weak moment. That's why the magnetization is falling. People don't know about the magnetic ground state of it. Some people are saying it's a reentrant spin glass, some people say cluster glass, some say super spin glass, and so on. And people don't know what is the origin of this exchange bias. So is it due to a mixture of antiferromagnetic and ferromagnetic phases, coexisting spin glass and ferromagnetic phase, or can be a standalone spin glass phase? So because the structural transition can give rise to a lot of disorder in the system, and we try to understand this magnetic properties of the system through muon and neutron diffraction experiment. And it was done in Rutherford Appleton Laboratory in the ISIS facility, and where the MEVSR was done on EMU and Hi-Fi instruments, and the diffraction was done on WISH. And so in MEVSR, we basically measured the asymmetry, and for a we allowed the positive muon to strike the sample, and I look at the amount of asymmetry that we are getting from the decaying positron. And anyway, people have already given a lot of talks on muon, so I'm not going into detail of that. Let us go back, let us go straight to the results. And most importantly, when you measure the muon asymmetry, so between the forward and the backward counts observed in the detectors, we see that this asymmetry follows a sort of exponential decay. And this exponential decay is very much pronounced in the ordered phase, which is obvious. And we measured both zero field MEVSR and longitudinal field MEVSR under 45 kilo of field, and it is seen that this this data cannot be fitted with a single exponential function, and we use a double exponential function to fit the data. And we found interesting thing here is that the that the asymmetry follows a very interesting pattern. So it exactly mimics what is there in the magnetization data. So the asymmetry is high at higher temperature, then it falls down when this long range order takes place, which is obvious when a ferromagnetism takes place, asymmetry falls, and then it rises again, which basically indicates that the loss of any magnetic order. And then beyond this TCM, it falls again. So this indicates that TCM indicate another magnetic transition, magnetic ordering. And when you go down to the low temperature, TB, beyond which the spin glass-like phase was predicted, we see a rise again. And so, what μSR tells us that there's a sharp fall in A0 below TC, and below the martensitic transition at TMS, almost full asymmetry is regained. So the martensitic transition actually drives the system from a ferromagnetic order state to a paramagnetic one. So there is no story of antiferromagnetism or anything. And then at TCM, once again, we find that we again find that this asymmetry again falls, indicating that the magnetic transition has taken place. And below TM, that there's a visible sluggish rise in asymmetry, which indicates that we are again losing some kind of magnetic order, and which indicates a glassy magnetic phase. But we don't regain the full asymmetry. That means this glassy magnetic phase actually coexists with some kind of an ordered phase. And this low temperature data between 30 and 150 K μSR data can be fitted with a some kind of a stretched exponential function, and a stretched exponential function gives this is given by that, and this beta value gives 0.33, which is very close to for the concentrated metallic spin glasses. So this is a kind of a concentrated metallic spin glasses, which is basically, you know, that the standard spin glasses where manganese is doped in copper, that kind of spin glasses it shows. And we have done the diffraction on the sample, and the powder neutron diffraction doesn't show any magnetic superlattice reflection at any temperature, indicating that there is no magnetic transition, antiferromagnetic transition present in the system. And it shows some kind of a phase coexistence between the high temperature cubic phase, which is austenite, and the low temperature martensite phase. And we've done all the calculations, and we found the magnetic direction of the magnetic moment. So we found that this magnetism at high temperature below TC is ferromagnetic, and and also below TCM, it is also the ferromagnetic one. And so what neutron tells me that the system is paramagnetic above TCA with a cubic L21 structure, and at temperature 275 K, this neutron powder diffraction indicates that both cubic and orthorhombic phase can coexist. And at 275 K, no magnetic superlattice reflection was observed, that the martensite is certainly not antiferromagnetic. And at 80 K, the system is found to be purely orthorhombic. Ferromagnetic phases associated with the 4O structure, this is a periodic structure. Again, no antiferromagnetic superlattice reflection. So even at the ground state, there is no antiferromagnetism. The long range order in both austenite and martensite at ferromagnetic in nature. So only thing is that in between them, at to some temperature range, the system becomes non-magnetic. And so we get to the final picture. So the ground state that we found from our μSR data is spin glass, and it is not a complete spin glass because we don't recover the full asymmetry in our μSR data. So it is possibly existing with an ordered FM phase. The spin glass has a re-entrant, so it develops out of ordered magnetic phase, and there is no long range FM order. It is the presence of Mn primed intersite short range correlation that gives rise to magnetic order. And the observed exchange bias that is observed in the systems are possibly due to the interface of ferromagnetic and the spin glass interface. And then there is a picture here where we are showing this orange part is some kind of a interfacial spin glass range, and these are some kind of ferromagnetic phases. So because there is structural transition, there can be a lot of basically structural domains, and at the interface of the structural domains, there may be possible that this spin glass like state coexist here. So this is our experiment has come in ISIS news also, where it says a combining insight from a neutron and muon to explain magnetic transitions. And I want to conclude my talk here. And before that, I have to acknowledge India RAL collaborative project, which has given me the beam time for muon and neutron experiment. And then we have ISIS facility where we've done the experiment. And this experiment was, I'm very much, I'd like to acknowledge Adroja, who is a long-time collaborator of mine, and my former student, Juma, who was also a postdoc with Adroja, who actually was present at the time of experiment, and my another former student, Shobhik, who is in UGC CSR Kolkata. He actually, during his PhD, we started working on these materials, and Shobhasachi, he prepared the samples, and the MUSR part was duly held by James Lord and Adrian Hill here. Thank you very much for your kind attention. Thanks.
Is there any question online? Any question you can have? No? So maybe I have one. It's very interesting that below monotropic transition, does it remain down to low temperature or it disappears at certain temperature? Because you see a paramagnetic state below monotropic transition.
No, it's a structural transition which takes place at a particular temperature only.
Yeah. So that structure remains. It remains down to low temperature.
It remains. No,
Yeah.
it's basically when the structural transition takes place, what happens that it goes from a cubic to orthorhombic, but this orthorhombic phase remains down to the lowest temperature.
Okay. It's quite interesting that you have a paramagnetic state below the ordering temperature.
Yes.
Below the antiparamagnetic. So it's very unusual.
Yeah, very unusual.
Yes. Okay.
Because,
thank you, Subhan. Yeah.
Okay.
Thank you. These results are published?
Yeah, it's published. Yeah.
Okay. So please communicate all of you, your publications to us. We need to upload in the web page.
I've already
communicated. I'm just generally saying for all the users online. So thank you very much. So let me thank all the speakers.
Sir, may I?
Second session.
May I ask one question, sir?
Yes, please. Who is that? Please
sir,
tell your name.
Krishnakant Dubey from IIT BHU.
Okay, yeah. Please ask.
Sir, my question is, what is the origin of the two relaxation rate for this particular compound, Ni2MnSn?
There are two different Mn sites. Yeah, there are two different Mn sites. Okay, there are two different Mn sites actually. One Mn is going into the regular Mn and another going to the Z site. I have shown it. So that is the reason for the two relaxation. Possible.
Sir, will they contribute same like they have almost equal moment?
They have almost equal, but one has a much stronger density. So regular Mn has a bigger density. If you look at the composition, so that is a much higher density of manganese. So that will contribute more. Okay.
Thank you, sir.
Thank you.
Yeah.
Thank you all. So now let us move on to the last one, discussion section. And I request Mr. Jayachandra to take over.
Good afternoon to all the participants from the West, and good evening to Indian and participants from the East side. This actually brings us to the close with a 24 jam-packed talks, and we thank all the participants and all the speakers. only the growing number indicates that there is a growing interest in using the synchrotron and neutron facilities. And we request the DST. Poonam, are you there? Okay. We request the DST to consider further extension of this work. With maybe new projects or new phase of the current projects. We have Dr. Poonam from the Department of Science and Technology Nano Mission. She has to say a few words, and then if there are any questions on the chat box, our people from here will be able to take these questions and request the speakers and others to respond. And Poonam, over to you.
Yes, thank you, sir. On behalf of DST, I would extend my regards and thanks to the organizers for providing this platform, for sharing the thoughts and experience of the users for the facilities. So this is the very first time we had such a meeting in which we were able to understand the thing what the users could get from by using those facilities which we have created through Nano Mission. So thank you so much. Regarding the 3 projects, the collaboration which we have for KEK Japan as well as for RAL UK, they have been extended up till 31st March 2022 with the existing budgets. And for the Petra, it will be running up till September 2024. So these are the current status of the 3 projects. But as far as DST goes, we have few points which I would like to share. The very first thing is that we are very happy to share that the user base for the KEK beamline has increased, and it's a good news for both sides. Secondly, we want to increase the number of users of the ISIS neutron and muon sources. So we have to work on that. So DST would request and all the collaborating institutes of the 3 countries to conduct some training and training programs as well as workshops for increasing the user researcher basis. So we want to have more people who will be using those facilities, and we would request the users who have used the facilities to introduce new researchers to those facilities, so we can have more people getting benefited from these facilities. Also, DST encourages areas other than material science and people who are working in other areas, maybe biological sciences or related fields, to use these facilities. For that, we need to work together to increase the awareness regarding these facilities which we have. So this is all from the behalf of DST. So we are very happy to know about the progress, and I'm very thankful to all the 3 coordinators and Sanyal sir and Sood sir. So from DST, it's all we have. Thank you.
Thank you, Dr. Poonam. Actually, Dr. Poonam is the person who helps us in getting the sanctions and monitoring these projects at the Nano Mission of the Department of Science and Technology. May I request Professor Milan Sanyal to say a few words, please? Professor Sanyal?
Okay, can you hear me?
Yeah, sure, sir.
Anyway, I was not expecting this question, but I thought I quietly will view this. But I must say that I'm very happy to see that the way utilization of these 3 projects are spreading over the entire country, and all different universities and institutes are doing it in a very nice way. And I must thank the Department of Science and Technology through Poonam our support from DST should continue, and this is an excellent program. I don't think we have any similar program where so many universities and so many institutes are involved in one platform. And this idea came from Milind Kulkarni and Poonam. So, to generate or to have this kind of meeting, and I would like to thank them and thank Jayachandra for organizing all this in a very nice way. I wish we could have a physical meeting with everybody together and discussing things. I'm sure in future that will happen, and we can take these projects further. And the new coordinators, 3 coordinators who are, of course, only Sundaresan is old one now, like me. But the Kanishko and Sebastian, they are taking over these new projects very nicely. I feel so happy that these projects are working out very nice. And Professor Rao was present yesterday in the morning. That's also a very encouraging thing to us. I will mention what Professor Ajay Sood mentioned, that now we have access to world's best facilities, both in terms of neutron and synchrotron. So the researcher from all over the country should think breakthrough results, whether we can really do some experiments where our results can be published in top journals. More and more so, because I'm sure few are already coming, but I think we must have more such papers coming out in the top journals of the world. With this, I have enjoyed since yesterday several exciting talks given by people from different parts of the country, and I'm so excited about these projects. Thank you so much.
Thank you, sir. Thank you for your kind words. We checked that in the chat box there are no comments or no queries or no suggestions. So actually this brings us to the once again Professor Kanishka Biswas has one question. Dr. Poonam probably may have to answer.
So hi, Dr. Jadhav. So I have one question. Like we are running that project. It's called All Synchrotron Neutron, and that was very popular throughout this country. I think Professor Chanel knows this very well. So and then I think we expect to have phase 2 of that as well.
Yes, sir. We have noted that.
Yeah. So because we can have access to world other base synchrotron and neutron through that project, and it was like the productivity of that the small project was huge, because we have published many good papers through that project and trained many good manpowers actually.
So we can work on this. We noted earlier also, so we can just have otherwise a discussion and we can work on that.
Then,
sure.
Poonam, I will tell you. See, we will give you the approval most likely by next April next year.
Okay.
Because this year we didn't have the money. Next year we will give you the approval once the regular scheme starts.
Okay.
Okay.
Anyway, this year it is difficult to travel in any case.
Yes,
so
yes.
That's fine. Yes.
Yeah.
It's thank you. Good to know that next year it will happen. Yeah.
No, because I think I take this opportunity to tell both Vinit Kulkarni and Poonam that it's good that Kanishko raised this point. Actually, when we do these 3 projects where we have preferred access to India for people who, and through these projects we generate new manpower, woman power who uses synchrotron and neutron. And then we test out whether they're good enough to apply for open general call for proposal and get time. So the projects which Kanishka is mentioning, this is the beam time is obtained by general application to APS and Diamond and many other notch synchrotron or neutron facilities. So that is why the other project is also very important for completeness. So I'm very happy to know that it will come next year. Thank you.
Can I?
Mr. Peter.
All in all, I mean, it was very nice program. We really enjoyed. As Professor Sanyal mentioned, anyway, we are going to travel next 1 year, most probably. And most of the faculty members actually presented the talks. Shall we have another meeting, probably focusing more students? I mean, they can participate and present their work, so that they can get some, and attention also. They are the future champions in the country.
Yeah, that should be the physical meeting. That's what we are waiting for this pandemic going away. So let us see.
So, do we need Milind to respond to this, Milind?
I don't know when we will be able to meet. I'm not sure when we will be able to meet. That is what I can say.
Physical meeting is difficult, sir.
All right. No, in principle, is it okay to have a workshop meeting like that?
Yes, sir. This is the one thing which Kulkarni sir also proposed, and we had this idea that we should work on workshops now to make people aware about the facilities and to have
Aware about,
more
yes,
space.
yes.
This was the thing which we just discussed.
Yeah.
Yeah. So
Thank
we
you.
can, in the meantime, we can work with this once the COVID situation is improved.
Yeah. I hope we are coming out with some proceedings of this meeting sometimes later. Am I right, Sebastian? Yeah. Yeah, we'll plan to do that. So this actually brings us close of this meeting. And if anyone has any questions, any comments, any suggestions, you can just come forward. If not, I would like to thank everyone, especially all the speakers. Very eminent people have given about 24 talks in the last 2 days. And actually, on behalf of all the organizers, we thank all the speakers who have agreed to give the talks and, be with us last 2 days. And Professor Milan Sanyal actually needs to be thanked because he's the person who's the originator of most of these programs and also keep guiding us in each steps. Professor Rajay Sood, D.D. Sharma, and Mrinmoy are always, giving us constant support. And as Milan Sanyal said, it is Milind Kulkarni and Poonam who have been, behind us to have a workshop of this kind, and the success actually goes to them. And thank you, Milind Kulkarni and Dr. Poonam, for your, for your thinking and also for helping us to implement these programs. I must thank all the participants all over the country and also people from abroad for having participated. In this number, we never expected that this number will be these many numbers will be there. And a special thanks to the JNC administration for facilitating us with the infrastructure. And I must specially mention Professor Sundaresan, Professor Kanishka Biswas, and Professor Sebastian. They have really worked very hard for making the program and also guiding us in various stages. The staff of the conference hall, Mr. Peer Munegowda, Dilip, Srinivas, have been very, very helpful in putting up the talks and also synchronizing various issues. And here I need to give a special thanks to our computer laboratory people and also Nabonita Guha, information officer, for having made that WebEx link possible. And the staff of the dining hall, housekeeping, and garden have really worked with us. And certainly I fail in my duty if I don't thank Dr. Shreya and Mr. Moinak for being with us and also helping us in various issues connecting to the speakers and also to the talks. And we hope that these kind of programs will be repeated in future with the guidance of Professor Milan Sanyal, DST, and other agencies. And with this, good evening and good night. Thank you very much. Thank you all.
Good night.
Thank you.
Good night.
All the talks are available in YouTube, JNC.
Oh yeah, okay.
Yeah.
Professor Sundaresan says all the talks are available, on the YouTube.
JNCASR.
JNCASR, yeah. Thank you all. Thank you. Good night.
Thank you all.
Okay, thank you.
Okay, thank you.
Thank you.